Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based course. And as always, it is an honor and a privilege to be serving you today, as it is every day here in my virtual classroom. Step on aside as we jump into section 3.8 of the Big Ideas Math Integrated Math 3 textbook on analyzing graphs of polynomial functions. Now, as I was skimming through the table of contents and just what each section would actually provide, I thought this was the one that would be the key. This is how we do the tableless graphing as a whole thing. And by and large, we're going to do a lot of it in this one. But we did some before. We did some in section 3.5, and 3.7 hit some, not in the same vein that I would have expected either way, but 3.5 actually began what we were starting and talking about when it came to x-intercepts, y-intercepts, and behavior actually started in section 3.1, although we used a table. And it looks like here we're going to use the graphing calculator here and there, because we're also going to be talking about relative maxes and mins when it does these turns where it hits these peaks. And for ones that you probably couldn't factor, or how just the book just expects you to use them that way. So if you want to follow along, jump to the description section down below and download this PDF and find the timestamps to each particular section you want to look for, whether it's these particular problems in the problem set or just with the lecture portion, which we're going to start right now. So I'm going to go ahead and begin that with you here. We are going to use x-intercepts to graph polynomial functions. So whether it's already in factored form or we need to factor it, whichever one they provide for us, we're going to do that and cross through them, including multiplicities, I suppose, is needed. Use something called the location principle to identify zeros of polynomial functions. It's going to be a pretty straightforward process that we use, but it's the graphing calculator we're going to have to use for that. And graphing calculator here as well. Find turning points and identify local maxes and local mins of graphs of polynomial functions. So I kind of just mentioned that in passing a second ago, but we have functions that are going to be doing this kind of stuff right here, right? Well, the turning points right here, we've mentioned ideas of where they can turn and such, specifically the bounce off right here, but the actual location was never certain. Well, the graphing calculator can find those. Calculus can find it as well, but we're not in calculus. We're not going to do that. And identify even and odd functions. Different than even degree and odd degree when it comes to vocabulary terms. This has to do with symmetry across axes, y-axis, and the origin, actually. And we're going to get to those when we hit them. All right, here are some new phrases: local max, local min. We're actually talking about these as local mins and maxes, just so you know. There's a difference between local maxes and mins and absolute maxes and mins, just because this goes up and down forever. I want to make sure you note that. And even an odd function, again, not to confuse with even degree and odd degree. All right, graphing polynomial functions. A lot of this stuff might sound like things we've already heard, seen, or done. In this chapter, you have learned that zeros, factor solutions, and x-intercepts are closely related concepts. For me, I almost say that they're synonymous with each other. Factors, slightly opposite. There's another word, root, that is not here. But anyway, here's a summary of these relationships. 0. K is a zero of the polynomial function f in this scenario here when you have a polynomial. That means you're going to have the equation say f of x equals, and then you need to set it equal to 0. Factor is when something's in factored form, and then the zeros exist within the factorization right there. Solution is when you have the equation already set equal to 0 and they ask you to solve for x in that scenario. It's not always set equal to 0, but when they're asking you to, that's what you generally want to do, set it equal to 0. And then x-intercept is the value of x when y equals 0. So when you find that value, that's what it is. That's why they're all closely related. That's why I call them synonymous with each other. There's the other word, root, that's not on here. That would mean the same thing to us as solution or x-intercept or 0 in that way. So, using x-intercepts to graph a polynomial function. Let's graph this function f of x equals 1/6 times x plus 3 times x minus 2 quantity squared as a quantity. Now, they still use a table in some way. I kind of want to refrain in some ways as well, because my goal really is to work end behavior, x-intercepts, multiplicities, and that kind of stuff. Now, x-intercepts are going to be -3 and 2 because of factored form, revealing if y equals 0 that you get -3 and 2 here, so we can plot those points. At 2, there's a multiplicity of 2, as you can tell right here. I don't know if they mentioned it. I'm trying to see. I don't see them actually mentioning it, but because, you have a multiplicity of 2 here, so it's going to have that bounce off feature, whereas at -3, it's just going to cross through more in a linear sense. There, and it has to turn around at some point to make that happen, and we know we start from the bottom and end at the top because it's a cubic function. We know it's a cubic function because this is an x times an x squared. That makes it an x cubed cubic function. and then the 1/6 is a positive number, therefore that happens as well. Now, the last thing I'd want to point out is the y-intercept. So I will find one value for you, plug in 0 and see what you get out. And you plug in 0 really easily. It's 1/6 times 3 times -2 squared, or 4. 3 times 4 is 12. 12 divided by 6 is 2. So personally, listen, I'm probably not going to use tables on these things. I know they're talking about it, but they talk about it in other things that I've done tableless graphing for, quadratics especially. So I'm not going to use a table. What I am going to do is when they get to other problems where they ask you to graph that aren't in factored form or are unfactorable, or they say use a graphing calculator, I'll use those to end up sketching that graph. If we have to use a table for that, we will. But end behavior is stuff. Let's see, did they ask us to determine it? No, they just said graph it. But the end behavior is noted that as we go left, we go down. As we go right, we go up, as a result of this being a positive cubic. So those are a lot of things we spoke on before. Sorry if it felt like a rushed job when I spoke through that all. But outside of use of table, all that stuff can be covered by us because of what we know about this material right now. Okay, the location principle, this time we are going to use a graphing calculator for it. It's a pretty straightforward process. You can use location principle to help you find real zeros of polynomial functions. And the core concept is like so. If f is a polynomial function and a or b are two real numbers such that f of a is less than 0 and f of b is greater than 0, then f has at least one real zero between a and b. What they're saying is polynomials are continuous, and if you're going to go from negative to positive, somewhere in between you have to hit a 0. That's what they're telling you. And the reason why they're talking about this is because if you use a graphing calculator and you go through a table of values to find the real zeros of something, and there's more than one way to do this, you can use it on the graph or in the table. If you want to seek out real zeros, if you look at this table right here, this is the actual table of values for this, plug in 0, you get -6, etc. You'll notice that between 1 and 2, the y values go from negative to positive. If they go from negative to positive, that means somewhere in between x equals 1 and x equals 2, we hit y equals 0. That is a must need. Polynomial functions are continuous. It doesn't just jump from negative to positive. It actually flows from negative to positive. So somewhere between 1 and 2, and that's what they're saying, somewhere between 1 and 2, there is that value. So let's see what they're going to say here. Because f is a polynomial function of degree 3, it has 3 zeros. The only possible rational zero between 1 and 2 is 3/2. So the idea here is, yeah, we're going to use synthetic division on this. We can use our p's over q's. 3/2 is the only number that appears in our set here. Factors of 6 over factors of 6. So 1, 2, 3, and 6 over 1, 2, 3, and 6. The only one that actually appears between 1 and 2 is 3 over 2, positive 3 over 2. So that we know that as a cubic that must be the zero that it crosses. You can do some things to the table to break that down and find out exactly where it is, but as far as the rational zero, positive 1.5 appears to be that number. So if x minus 3/2 is one of the things, use synthetic division on that and you end up getting this other polynomial. Factor the 2 out of here and distribute it. Oh, they never did distribute it. Normally I'd distribute it into this guy. I guess they don't, only because they know that 3/2 is one of the x-intercepts you have to find anyway. Normally I would. But this quadratic factors now to 3x plus 1 times x plus 2. Not getting deep into the idea of how things factor. But that means that you then also have another root of -1/3 and of -2. Now you can, of course, still use rational root theorem on this thing alone to figure things out. But instead of testing every number under the sun, 3/2 would have taken forever to get to. I guess -2 was also one of them. But 3/2 would have taken forever to get to find that one. So I don't know how they're going to ask us to do it. They're going to say use location principle. I guess we're just going to have to make a determination with table. You know, we're going to play with it in a certain way. We're going to use the table and talk about it. So we're actually doing other practices. Right now, it's not just about graphing. It's about doing a practice. Location principles, one of the understandings of practice we're going to use. Turning points. Another important characteristic of graphs of polynomial functions is they have turning points. Now, you'll see me all the time say something like, a graph that starts down and finishes down might look like this. I don't know exactly if it's going to look like that. And that's true. I don't know exactly if it's going to look like that at all. It may have turning points like that. It may end up just doing something like this. It may do something straight up, just look more like a parabola, just like this, right? Or, you know, the heights might vary and it might have something like this. I don't specifically know what it's going to do in any such way, but if something starts down and finishes down, it has the ability to turn in between. And when it does turn in between, it tops out and bottoms out at certain parts like this. This is just of things of even degree, negative leading coefficient. But the turning points are called local maxes and local mins. Local maxes and local mins. The y-coordinate of a turning point is a local maximum. So in green, let me do it in green. In green are examples of local maximums. This is a local max. These are local maxes. This is a local max. These are local maxes right here. Anytime that it tops out at points where it has to go from increasing to decreasing is a local maximum. Whereas a local minimum is the y-coordinate of a turning point that where it's lower than all the other points around it. So that's a local min, and that's a local min. I guess for my specific graphs, those are the only local mins in this case. Nothing else is a local min. These things go down forever as well, so it has no absolute minimum. I guess we're not talking about that. But the turning points of graphs help determine the intervals for which a function is increasing or decreasing. If you hit a local maximum, you know it's going from increasing to decreasing. You hit a local minimum, you know it's going from decreasing to increasing. So we know the intervals, the values of x for which we go from increasing to decreasing, etc. And we can use a graphing calculator to do this. There's more that I want to say about it. We'll see what they're going to talk about it right here. Turning points of polynomial functions. The graph of every polynomial function of degree n has at most n minus 1 turning points. That means a linear function of degree 1 has 0 turning points. A quadratic function can at most have 1 turning point. A cubic function can at most have 2 turning points. Now, they say at most because it doesn't have to. How many times have you guys seen cubic functions that just do this and don't have any turning points? Remember, this is not a turning point. It didn't have a local max or min. It never bottomed out or topped out, just continued on this path. This is truly two turning points. A quartic function, a 4th degree, you see them all up here. These can have at most 3 turning points. So it can always have 1 less, at most 1 less. Degree 5, 1 more, can have 4 turning points. 1, 2, 3, 4. So it can do something like that, right? Now, that's true. If a polynomial of degree n has n distinct real zeros, then its graph does have exactly n minus 1 turning points. So in order to hit the x-axis, the number of times that, the degree of the polynomial has, such as this quadratic, let me just use this one. This quadratic is degree 2, and it hits the x-axis twice. If it hits the x-axis twice, then it will hit its turning point. It needs to turn to do that. If this cubic function hits the x-axis 3 times, then it will turn twice to make that happen. The 5th degree polynomial, if it has, let's see if I can make it hit all 5 times. If it has 5 x-intercepts there, then it will absolutely need those 4 turning points to make that happen, right? So that's what they're saying for those parts. All right, to find turning points, we'll graph each function, identify the x-intercepts and the points where the local maxes and mins occur, determine the intervals for which the function is increasing or decreasing. So they say straight up, use a graphing calculator. When we have standard form equations, unfortunately, it doesn't look like we're going to get deep into the factoring of these. That's what I wish we would have done, but they're going to go more for some irrational solutions and talk more about you need to use the graphing calculator for the maxes and mins anyway. So use a graphing calculator to graph the function, you plug it in, and then you go and look at the graph. The graph of x has 1 x-intercept and 2 turning points. We can tell by looking at it. There's the x-intercept. Here are the 2 turning points. Here's a max, here's a min. Where are they exactly? We're going to let the calculator help us. There are features called the 0, max, and min to help find these. The 0 helps us find the x-intercept. This Mission Impossible thing in the background is very spasmodic. I apologize if that shot. John Woo, man, he knows how to do some slow motion stuff. But this thing is just a little over the edge, no pun intended. And with a lot of hair flow, very much pun intended. Okay, anyway, the zeros help you find the x-intercepts. The max helps you find any relative maximum. What you have to do, though, they're going to ask you to choose a left bound and right bound. It says find the maximum between your interval that you choose. So you want to make sure your maximum exists somewhere between your left and right bound like that. And the minimum the same way. Choose a left and right bound to the left and right of that minimum that you do. The x-intercept is around negative 1.2. Again, it's not exact, possibly irrational. Maybe, I think. And then there are exact local maxes and mins of these at 0, 6, and 2, 2. That's not always predictable like that. You're going to see a lot that are just at random places, and I think that's the point. But those are the x values of the maxes and mins at 0 and 2, and the actual y value of the maxes and mins are 6 and 2. So the intervals of increase and decrease are based off of whether you're at a max or min. A max means you, once again, go from increasing to decreasing, and a min goes from decreasing to increasing. So you can tell intervals for which the function is increasing to the left of 0 and to the right of 2. That's here. And it decreases in between 0 and 2. And then let's see what else they want us to do. Oh, here's the second part, second question. I'll go faster through this one. The x-intercepts this time, you use the 0 feature for that. There are these 4 values here. Looks like they're using 2 decimal places to round, so I'll do the same thing. The function has a local min at this value here and this value here. These are local mins. So you can see that they did rounding for these values here. They're not perfect. And like I stated, unless you're using calculus, you're not going to find these local mins without a calculator. So calculus or calculator. 3.96 and negative 43.04 was this other one right here. This one's a strange scaling. Sorry, this was a local maximum. I totally read the wrong word. The local max is this guy right here at this number. And the others were the local mins. So you can state decreasing on this interval and this interval, increasing on this interval and this interval. They have them written down. So we're going to have to do a lot of things there. Determine intervals, etc., local maxes and mins, a lot of different things to use. The last thing to talk about are even and odd functions. Now again, not to confuse with even degree and odd degree. An even degree function is something where the leading term is an even exponent. So even degree example would be something like y equals x to the fourth minus 3x cubed plus 2x squared plus 1, something like that. But that's not an even function. Not even function. So difference between even degree and even function. An odd degree example function would be something like something that starts with an odd exponent like that. So this might be something like that. That's an odd degree example, but that's not necessarily an odd function. Now, before I move on into what these things actually are, every even function can be made by an even degree function, and every odd function can be made by an odd degree function. Not everyone. I guess I'm saying the phrasing wrong. But not every even degree function is an even function, right? Every even function is even degree. There we go. Every even function is even degree. Every odd function is odd degree, but not vice versa. All right, in f, a function f is an even function when f of negative x equals f of x for all x in its domain. What they're telling you is that when I plug in some x value and get some y value out, plugging in the opposite x value gives me the same y value. Here's that example. Plugging in x gets me this y. Plugging in negative x gets me the same y. They're the same height. Same with here and here, and here and here, and here and here. That's the idea. Even functions have symmetry about the y-axis. You reflect across the y-axis, and that's what happens there. We know f of negative x as transforming something by reflecting it across the y-axis, and when the heights are the same, that's when your function is even. This even degree function doesn't necessarily have, and it doesn't have symmetry across the y-axis. That cubic function is actually disrupted, or the cubic term is actually disrupting that from being so, which is why that's happening. The next one is an odd function. This is where when you plug in a negative x out, you don't get the same y, but you get the exact opposite y. So understand that when I plug in some x and get some y out, plugging in the opposite x gets me the exact opposite y. So much so that you could draw a line from one to the other and it goes through the origin. That would be the same of this point and this point right here. Plug in opposite x, get opposite y. There's symmetry about the origin for odd functions. So that also means that as long as it's a polynomial, it will also go through the origin. When you plug in 0, you will get 0 out. So they say one way to recognize this is that it looks the same after 180-degree rotation. I don't know if they mentioned the first one here, but the first one is if you flip it over, look into a mirror. But if I take this one and I'm going to try and do this here. Give me 1 second. I'm trying to copy and paste it here and shrink it down to size. I will literally flip this thing over and you get the same thing back out so long that you stay on the same axes here. So here's that example of an odd function in practice right about here. So let's go ahead and rotate this thing over 180 degrees and you get the same thing out if I had this lined up perfectly. right? So that's an example of an odd function. This isn't an odd function. This even term is actually disrupting its flow from being so. It's odd degree, but it's not an odd function because it doesn't have perfect symmetry about the origin. So you can do these tests without the graph. You can do the tests with a graph in either or case. Without the graph, it's very simple. What you do is you substitute negative x in for x in these polynomials, and then you determine whether or not you have the exact opposite and or the exact same y value as you did before. If you have the exact same y value, it's an even function. If you have the exact opposite y value, it's an odd function. If you have neither, it's a neither case. For polynomials, there's another trick in the book, and I'll state what it is in the problem set. I kind of teased it here. I kind of teased it here and here that made this not even and not odd. So there you go. Because I want you to do the practice that they talk about first. Determine whether each function is even, odd, or neither. Oh, and the main reason for that is because not everything's a polynomial. You have to be able to do the test when it's not a polynomial. Anyway, I'm going to tell you straight off the bat, I know this one's odd, I know this one's even, I know this one's neither. So let's see if we can figure this out. You plug in negative x into here, negative x cubed minus 7 times negative x. What happens when you raise negative numbers to odd powers is they change their sign. So this does become negative x cubed, and subtracting negative 7x becomes plus 7x. Now what they do from there is they factor out the negative, and the important reason for factoring out the negative is to represent what's inside as exactly what it used to be. Remember, f of x was x cubed minus 7x. Now f of negative x is the exact opposite of x cubed minus 7x, which means it's the opposite of the previous f of x value you had. If that's the case, that means you have an odd function. So do factor out that negative and see what the result is if that's what you're looking to do, specifically when this term was positive and now it's negative. Now let's look at the next one, as that was an odd function. Second one, plug in negative x into these. When you raise a negative number to an even power, they'll turn positive. So negative x to the positive fourth, or negative x to the fourth is positive x to the fourth. Negative x squared is positive x squared, and this negative 1 doesn't get a substitution and change. Because this is the exact same as this, that means plugging in negative x gets me the same y. It means we have an even function. Now listen, I could substitute 3 and negative 3 into my equation and see if I get the exact same y and exact opposite y. And that is showing by example that a function may be even or odd, but it's not proving by example, because you could get what's called a false positive, which means I could plug in 3 and get 9 and negative 3 and get 9. But that doesn't guarantee that when I plug in 4, I get the same y values when I plug in negative 4. It might change here and there. And this is saying for every x in your polynomial. That's the idea behind this. Anyway, this one's an even function because you have the exact same y here as you have right here, the exact same function. They are the same. And now replace x with negative x in this last equation here, where you plug in negative x cubed is negative x cubed. The plus 2 doesn't change though. So as you'll notice that when you factor a negative out of this one, you actually just get negative, when you factor negative out of this one, you get x cubed minus 2. And that's not the same as x cubed plus 2. As far as being the opposite of, and this isn't the exact same as that. So because it's not even and it's not odd, it's a neither case. It just means, which most of our polynomials are neither cases, but for the sake of test, you're probably going to see a lot of evens and odds. But it's just a way of stating that it's neither symmetric across the y-axis nor symmetric about the origin. That's fine. Okay, that is the end of the lecture portion. Let's go to the vocabulary and core concept check, numbers 1 and 2, and then we'll get on to our problem set. I think, well, let's see. We're going up to problem 55. Number 1, complete the sentence. A local maximum or local minimum of a polynomial function occurs at a turning point of the graph of the function. So again, a polynomial does this. Local maxes are here, local mins are here. These are turning points of your function. Number 2, explain what a local max of a function is and how it may be different from the maximum value of a function. Yeah, we have referred to maxes before. This time I called them absolute maxes. And by the way, because some books treat some things differently than others, let me just type something to have it there in place. Local maximum is also known, if you look it up or if you see it in other books or websites, as a relative maximum. Same with local min and relative min. So local and relative are both the same adjective for this noun right here, okay? Also, Maximum, when they are talking about maximum here, they're either talking about what they most often refer to as the absolute maximum or the global maximum. So when it comes to phrasing, specifically in calculus, they'll either talk about relative maxes or relative maxes mins, local maxes mins. That means the same thing. Absolute max mins, global max mins means the same thing. When they say max and min, by the way, they all mean the word, one general term for both the words max and min at the same time is extreme. A local extreme, a global extreme. Either find all the relative extremes. They're finding all the local maxes and mins. Stuff like that. Anyway, I just want to state that before we move on. Explain what a max-min function is, local max-min, and how it may be different from the maximum value of the function. So a local maximum is a turning point, but not necessarily the highest point of the function. Turning point in that it is higher than the points around it. It's where it goes from increasing to decreasing, but it's not necessarily the highest point of the function itself, like an absolute maximum would be. This graph that I just drew right here actually doesn't even have an absolute maximum because it goes up forever. It doesn't have one. Let's say it turned one more time right here and went back down like that. Well, these are 1, 2, 3 local maximums, but this is also the absolute maximum because that's the highest this graph ever goes. It goes down forever after that, right? Anyway, they are 1 and 2 were just very specific about those two things. They didn't talk about evens and odd functions. They didn't talk about anything else there. So, we'll just leave it be. All right, guys, we're going to get into the actual problem set. So get ready, graphing calculator. We're going to have to do some graphs and things as well. Download the graph stuff below that I'm going to provide for you. I'm probably going to use the scaled graphs on these ones because my goal isn't really to use tables on these to do the majority of these graphs. I can change scales as need to as well. Okay, let's go ahead and get started. In exercises 3 through 6, match the function with its graph. So on number 3, and here's what I'm going to do, guys. I'm going to do a rough sketch of the graph, and then I'm going to do the match afterward. F of x equals x minus 1 times x minus 2 times x plus 2. Now, when it comes to this rough sketch, I want to identify the following things here. First of all, if I multiplied all these out, which I'm not going to, but if I multiplied all these out, my leading term would be an x cubed. An x cubed means this is a third degree polynomial, which also means positive. That's the thing we care about. It's a third degree positive. That means, and the stretch factor is 1, which is positive. Sorry. I'm saying different things. Third degree is odd. Third degree is odd. The leading coefficient is 1, which is positive, which means this graph will start down and finish up. Whether it turns in these points is, I don't know. That's uncertain at this point. What we will find out very soon, and right now, is, I don't want to use red. Let's use green. Is the x-intercepts are revealed by the zeros here. This x-intercept is 1, this one is 2, and this one is negative 2. So what I'm going to do here, we understand the end behavior. I'm going to give you a rough sketch of this graph. So we have at 1 and 2 and negative 2, we have x-intercepts. If you wanted to know about y-intercept, you would substitute 0. Let's see, y-int. We would substitute 0 for x. 0 minus 1 is negative 1. 0 minus 2 is negative 2. 0 plus 2 is 2. Negative 1 times negative 2 is 2 times 2 is 4. So this thing would touch up at 4 like this. And this can help complete your graph. It will have the start down, finish up idea. We're looking for this graph that goes like that. So the graph that goes like that crosses at negative 2 and 1 and 2 and a y-intercept of 4 looks to be A. Number 3 is A. Now, I'm not going to do sketches for all of them. I wanted to start with this one to get you the understanding of how we're looking for the answers to these questions. And that's what I was seeking out for this thing on number 3. Let's go to number 4. Now, number 4 has, because it looks like a lot of these are kind of similar-esque, so I can't speak too heavily on each individual part. Here are the things that are all the same. They're all cubics, because if you expand these out, you either have an x times x times x or an x squared times x or something like that. They all have a leading coefficient of 1, which is a positive number, which means they're all cubics. You can see this right here. They all start down and finish up, etc. The difference is, what are the x-intercepts? Technically, another difference is what are their y-intercepts, and also what are the multiplicities. So let's at least look into x-intercepts and y-intercepts together. I'm not going to sketch the graph. I'm just going to find the one that works out. There's -2 and -1. Now at -2, it has a multiplicity of 2. Multiplicity of 2 means the graph will bounce off of that x-intercepts right there instead of going through it. So which ones do that? And then we'll confirm the y-intercepts with it as well. Obviously, A was already taken care of. B, no. C, it does bounce off of that -2 indeed. It might be C. D, it doesn't. Yeah, I think it's going to be C. The graph's going to be C like that. Now, if you want to confirm something else, let's look for its y-intercept. When you plug in 0 into here, you get 2 squared times 1. 2 squared times 1 is 4. Does this graph have a y-intercept of 4? It sure does. Right there. It sure does. And because of that, that looks like it's going to be the graph of C. Okay, number 5. Let's see if we can say these ones out loud. I will still write the function with it, and let's make note because it's either one or the other. Positive cubic function, once again. Because listen, we're going to draw our own graphs, I think, coming up next. So I don't want to do too much here. X-intercepts of -1, 1, and 2. No multiplicity, so it'll go through all of them. So -1, 1, and 2 looks to be B right there. Whereas this one has a different story and a multiplicity involved. This one also seems to have a y-intercept of -2. Would this have a y-intercept of -2? 1 times -1 times 2. Yes, that's a y-intercept of -2. So this graph is B. And finally, looks like we're going to get D. Let's see how we do get D from number 6. On number 6, we have f of x equals x minus 1 quantity squared times x plus 2. If you notice, we have x-intercepts of 1 and -2. This is 1 and -2. How can it only have 2 of them? Because it bounces off of one of them because it has a multiplicity of 2. It bounces off of 1 like so. Boom, and it hits that. Now, does it also properly have a y-intercept of 2? -1 squared times 2 is 1 times 2, which is 2. So yes, that one's also confirmed. So that answer is D on number 6, and it looks like we have all these graphs taken care of. Now, I did mention on number 3 things like degree and leading coefficient and how we can use these to get end behavior. Those will apply for the questions after, given that all these were cubics and all these graphs kind of have that similar-esque thing. Then we had not much to say on those ones. The next ones, I think we will. Okay, number 7 through 14, we will graph the following functions. This time it's on us. And like I said, I'm going to go much more of a tableless route, meaning if I don't hit exact local maxes and mins and stuff, I'm going to feel okay. If your teacher asks you to get those table things, go ahead. But my goal is to talk about x-intercepts, y-intercepts, and behavior. X-intercepts with multiplicities, y-intercepts, and end behavior. And then we can draw the graph as a general idea, even if we don't hit all exact points the entirety of the way. All right, so f of x equals x minus 2 quantity squared times x plus 1. Now that kind of looks like these questions right here. Not exactly, but it is close enough, because what I mean by close enough is this. The degree of this polynomial is 3. X squared times x is x cubed. That makes it an odd function. The leading coefficient is 1. That makes this a positive. So that means start down, finish up, right? We know that much. We also know, or we also can determine the x-intercepts as 2 and -1. At 2, it has a multiplicity of 2. That's how I'm going to put it, multiplicity of 2. That means it'll bounce off of that 2. And the y-intercept, when you substitute 0 for x, 0 minus 2 is -2, squared is 4, times 0 plus 1 is 1, 4 times 1 is 4. So this is the information we need for the graph, x-intercepts, y-intercepts, and all. Let me get my graph, copy, and paste. And let's go ahead and get a sketch of this. Again, the part that I will not qualify exactly on this is every point that's not the critical features, but we will get all the end behavior that we want out of this guy here. So we do have a y-intercept of 4, x-intercepts of 2 and -1. We are going to start from the bottom and finish up. So, and it's going to bounce off of 2. It's going to bounce off of 2. So somewhere this graph needs to do something here. Now listen, we don't know if this is a local max or min, right? I can't guarantee in any such way. That's the part that it's It's going to get a little screwy on these graphs maybe. That maybe I don't get that part perfect. But this should bounce off of this and finish back up, right? We understand the end behavior is that we know it can't just go through like this because otherwise it would finish down, or you'd have to go back up and through an x-intercept that never existed. So that is why the bounce off exists how it does, given the degree of 2. We can use that. That's the graph. That's all they ask for. I'm moving on. Your one at the table will look similar-esque. It's going to look close enough to what we're getting as a general thing. Again, go ahead and use a table if you prefer to, or if you're required to. Number 8. F of x equals x plus 2 quantity squared times x plus 4 quantity squared. X squared times x squared is x to the 4th. This degree is 4. That makes it an even function. The leading coefficient, once again, is 1. 1, you can't see the number. That makes it a positive. That means this will have a start up, finish up kind of scenario like this. I don't know exactly how it's going to hit yet. I have ideas. We'll do that. Let me take care of hiccups here really fast, though. Okay, we'll see if I fixed them. Okay, x-intercepts. Let's use green. X-intercepts are -2 and -4. Notice because both of them are squared, they each have multiplicities of 2. Multiplicity of 2 here, multiplicity of 2 here. That means we will bounce off of both -2 and -4. So the graph is actually probably going to look more like this. Well, I guess I need to rotate the... boom. It's going to bounce off of 2 different x-intercepts over here. It's not going to look slanted like that, but that's the idea. The y-intercept is going to be 2 squared times 4 squared. 2 squared is 4. 4 squared is 16. 4 times 16 is actually 64. This graph goes super tall. Now, I'm still going to be using this scaled graph axis stuff as it is, but I'm just going to change the scale of y. And honestly, listen, I don't even need the bottom part of the graph, so I'm just going to do it like this. Let's make these go by 8s. Whatever, I'll call this one 64. So that's 64 because this is 80. Hey-oh, and this is 40. So 40, there's 64 like that, right? So if that's 64, that is our y-intercept. Our x-intercepts are -2 and -4. And this starts up and finishes up. So it needs to bounce off of those 2 sets of points here. It bounces off of -4. It has to come up somewhere. I don't know where that actual top is. That's the part I'm missing out on. You can plug in -3, get yourself an idea. It'll bounce off of -2. It'll come up through this guy right here, and it'll finish upward like that. Looks like a tooth we got to pull. Not the best look of a curve. Again, if I do another time over, maybe I can improve on it. Maybe a little better looking. But yeah, so that could be the idea of that graph on number 8. Number 9. And these are all in factored form, at least as factored as we can get. So we'll use that. Number 9, h of x equals x plus 1 quantity squared times x minus 1 times x minus 3. X squared times x is x to the 4th. This degree is 4. It's an even. A positive 1 leading coefficient, which means positive. Once again, start up, finish up is what we're looking for right here. X-intercepts are -1, 1, and 3. At -1, we have a multiplicity of 2. Once again, it's going to bounce off of that. The y-intercept, and there's always only one y-intercept. Plug in 0 for x in these. 1 squared is 1, times -1 is -1, times -3 is 3. So this graph, we can probably scale normally, as before. Shrink it to size. Okay, so for this one, we have our x-intercept here. We have our y-intercept here. We have a start up, finish up scenario. We will bounce off of the -1. So everything should agree with each other. Otherwise, if it doesn't, something went wrong. It should be coming up like this, hit itself back down. Maybe that's the local max. It's got to go through this time, not a bounce off. It's got to go through here, down here, and find its way back up here and through to finish off its end behavior going toward positive infinity. Never vertical. I'm just getting what I can through those bits of points. And there is our function. Our feature function. Number 10. And after number 10, I feel like I'm going to write less information, at least for the degrees and stuff. You'll see me whittle things down over time. g of x equals 4 times x plus 1 times x plus 2 times x minus 1. X times x times x is x cubed. We have a third degree polynomial. That's an odd function. The leading coefficient this time is 4, but it's still positive. So this will start down, finish up, whoop, like that. Okay. We have our 3x-intercepts at -1, -2, and 1, all with multiplicities of 1, so they'll just go straight through them, like that. And the y-intercept, you have to substitute 0 for x. Remember, 4 is a part of it. 4 times 1 times 2 times -1 is -8. -8. So there's our information. It is vertically stretched, right? That's where that -8 kicks in. If the 4 wasn't there, it would just be -2 as a y-intercept. So it is a vertical stretch still. But because it's positive, it doesn't change. It doesn't flip over or anything like that. So on this guy, we got -1, -2, and 1 here with -8 as the y-intercept. And it starts down and finishes up. So I got to find a way. This is going to be super stretched vertically, right? Super tall. Maybe I can make it go up high. I don't know how high it actually goes. Let's just pretend it goes up to there. It's got to go back down through here. It's got to hit this. Maybe it bottoms out there. Maybe a little bit of symmetry. And then it goes back up through that guy like that. It's possible that this thing probably would have topped out even at +8. You know, like that. To bottom out on that stage right there. I don't actually know. Just giving you the idea. And there's your cubic. Super tall and whatnot. Okay, number 11. H of x equals 1/3. So a vertical compression, right? But still positive. H of x equals 1. Oh, I always wonder. I'm like, why does that look weird? Because I didn't write the number. H of x equals 1/3 times x minus 5 times x plus 2 times x minus 3. Okay, let's write a little less this time. The degree is x cubed is odd. The leading coefficient, +1/3, is positive. All right, that's a little less for us, yeah? Odd cubics start down, finish up. We know that. X-intercepts, I'm not going to change what I write for those. I think I use them as much as you do. 5, -2, and 3. Probably good to write them in order, but I didn't. Y-intercept, -5 times 2 times -3 is 30, and 1/3 of 30 is 10. So we got a y-intercept of 10. And this is vertically compressed. It would have otherwise been 30, right? So I'll still try and not change the scale. Let's just kind of leave it as is, even though it's going to top out at that value. At least the x-intercepts are a little farther out. Gives me a little more character in my graph, I suppose. Well, that one's not really. But this y-intercept here is up at 10. It's got to start down, finish up. I think these parts will agree with each other pretty well here. So here, we start from the bottom. And then we come up and through here. Maybe it even goes past this a little bit, right? And then it can come down through here and back up enough. I do want to keep reminding you that local maxes and mins do not have to occur at y-intercepts. Even if you force it by appearance, that is probably why use of a table is an ask of us. It's not asked of us here. They said draw the graph. I'm getting you the essentials. Number 12. G of x equals 1/12 times x plus 4 times x plus 8 times x minus 1. Once again, we have... Listen, none of these are flipped over. I'm now looking... I didn't realize... I wish that they flipped some of these things over so we could talk about end behavior going the other way. Doesn't look like they're doing it. Doesn't even look like they're doing it in some future problems after this. I wonder why. I was really hoping for a lot of different kinds of problems here. It's... I'm mid on it. I'm mid on it. Anyway, yeah, degree, x times x times x is a cubic, right? I'm not going to write it this time. It's a cubic and positive leading coefficient, start down, finish up kind of thing. Let's just talk about the x-intercepts, the y-intercept, and do that end behavior for the graph. So x-intercepts are -4, -8, and 1. Y-intercept, 4 times 8 is 32, times -1 is -32. -32 over 12 reduces to negative... I had it and I lost it. 8 over 3, -8/3. Not a pleasant number. That's just the vertical compression nature. -8/3 is -2 2/3. So I'll still kind of plot it. At least it's still a point on the graph, right? One bit of the table that we will have. So -8 is here. We got -4 and +1. We hit -2 2/3. Right there is a y-intercept. It starts down, finishes up. So it starts from down here. has to hit a turning point, local max. Now listen, here's what you, oh, I just did something by accident. Here's what you shouldn't do. You shouldn't take this, and I mentioned this, you shouldn't take this and suddenly just curve it down like that and up like that. It doesn't have to fit in that way. It's likely the graph goes down somewhere to some minimum, then has to come back up and hit those points. So let's try something more like that, where it goes down through there, has an upward turn through that to kind of finish its process, right? Give it more of an appearance of symmetry that it deserves, that it seemingly deserves, right? I should probably even do it more like that if I could. So probably something like that. Again, this is without use of a table. Then give more respect to the graph where you can. Please, please. Number 13. Okay, 13 is interesting. Looks like 14 is interesting as well. And the way that they provide this extra quadratic portion is as a result of either the solutions are, it's not factorable. So the solutions may be irrational. They may be imaginary. X squared plus x plus 1. That discriminant, b squared minus 4ac, that's an imaginary result. I think on this one, it's probably beneficial to use more of a table because I can't do as many on the turning points here. Now, x times x squared is still an x cubed as far as leading term. It's still an x cubed. It's still a cubic. It's still a leading coefficient of a positive 1, things like that. But the only x-intercept that's truly here is 3. Now, y-intercept, we can plug in 0 for x still. Y-intercept is negative 3 times 0 plus 0 plus 1 is negative 3. So those are the only 2 points that I officially have. My guess is it'll have some turning points with the rest of this thing. Do I know where they are exactly? We'll kind of take a look with respect to the graph. We'll see if a use of table is necessary, but the problem with these other 2 solutions in this cubic is they are imaginary. They're a complex conjugate pair. So they are not crossing the x-axis, but they may still turn. They still change the behavior of your graph in some sort of way. So these points are hit like this, right? And this is a multiplicity of 1, and it starts down, finishes up. So what does this mean? Well, I'm trying to think about it. What this means is the graph probably does something like this. And I don't know specifically. I'm going to have to take a look. I was trying to think, how do I cross through here? Do I have to do that? No, that goes a little far out. It probably does something like this. It probably hits some local max, turns back down to hit this thing, and comes back up through here like that. So it's a local max around here, but it doesn't hit the x-axis. Hits a local min around here, doesn't hit, it hits a local min, and it goes back through the x-axis just in that one point. Do I know specifically? No, this is where a table could be of use. I'm going to go to the graphing calculator and see if I have anything near what it was supposed to be. Obviously, I don't know where the x's go in a specific way. Again, table's probably preferred for a question like this. I do agree. But my time crunch sense says you use a table as needed. I'm going to plug this thing in and see actually what it's going to look like. And if mine is close, I'm going to keep it. So x minus 3 times x squared plus x plus 1. Oh, never mind. I was going to say something, and now I don't need to. All right, let's look at the graph. Close. It's close. It looks like it kind of nearly topped out at that thing, but the idea's in place. That's where the turning points are. So if I were to kind of tweak this a little bit, I could probably do something a little more like, I mean, the end was pretty good. I think I was a little too far away from this part. So it looks like it does a little bit more of topping out at that y-intercept. Okay, that's fine. Maybe not having to bottom out so deeply, though. Just like that, kind of finding its way back up. So that idea is there. That's what it does. That's why it does. My other graph probably looks better. All right, there is number 13. Let's go to number 14, and it looks like 14 has the same issue. So we'll try the same thing here because those would be imaginary solutions. I can tell you straight up just by looking at the b squared minus 4ac of it all. But number 14, we have an f of x equals x minus 4 times 2x squared minus 2x plus 1. Okay, x times x squared is x cubed, still a cubic, odd degree. Leading coefficient will end up being 2. When you multiply everything out, it's going to be a 2x cubed. 2 is still positive. But that 2 doesn't affect your overall y-intercept, so we'll get to that. The x-intercept is 4. The y-intercept, because remember, these are imaginary. Y-intercept, you plug in 0, you get negative 4 times 0 plus negative 4. So yeah, I think it's just a little bit more of the same on this one. A little bit more of the same. Maybe some form of vertical stretch is in play, just given that there's that 2 involved as a whole. But 4 is here, negative 4 is here. It is a positive cubic, So I imagine you're still going to have something where maybe it tops out around here again. I'm not so certain. Maybe. But it's got to come back down before it finds its way back up, given the nature of this cubic. How deep does it go down? I don't know. Graphing calculator can help us with that. We'll take a look. So that's my idea of the graph, and if I'm near close to it, this is the old graph. If I'm near close to it, I'm going to go ahead and use it. So let's see what x minus 4, I did that again, x minus 4 times 2x squared minus 2x plus 1 is. It'll probably be a little taller, so we might, okay, so we don't see its bottom truly. But yeah, my graph is pretty much like that as well. If I zoom out the bottom a little bit, it's negative 20 or something. You'll at least see its local minimum. So this is kind of the appearance of my graph, and you can see once again, the y-intercept wasn't necessarily the turning point. Closer maybe to x equals 1, you had more of it right there, and it goes down like that and then back up. Okay, whatever. But it still does what it does. That's the appearance of the graph, and I'll leave it be. Okay. Numbers 15 and 16 on error analysis, and they're doing a lot of cubics. Describe and correct the error in using factors to graph f. So on number 15, they have x plus 2 times x minus 1 quantity squared. This x-intercept is 2 and negative 1, whereas they should have had negative 2 and positive 1. Now, also, their turning points, well, their turning points are probably based on what they called a negative and stuff like that. Because the bounce off should be where the 1 is. So they have basically their signs are off. Their x-intercepts are the opposite signs of what they should be. Instead, it should be at negative 2 and 1, and for negative 1 with the multiplicity of 2. Now, again, I think they kept that in mind. It's just that their graph was a reversed state of what it should have been. So if we fix this graph, and I'm only doing, again, the basic nature of it, not all the exact points. Oh, y-intercept, by the way, y-intercept here would have been 2 times negative 1 squared is 1. 2 times 1 is 2. Y-intercept should be up here. The fact they crossed at negative 2 is also a mistake. So if you note that your x-intercepts, once again, are negative 2 and 1. This one has a multiplicity of 2. And your y-intercept should be, instead, 0 plus 2 is 2. 0 minus 1 squared is 1. And that gives you 2 times 1 is 2. Then you'll see that the graph should do this, this, that. It should start down, finish up. It's a positive cubic. So it's going to probably come up through, just like theirs is. It's probably going to come up through somewhere before it hits that intercept like that. Then it's got to come down, bounce off of the 1. And then come up and through like that, and that should be our function instead. Still the right end behavior on their end, but the wrong x-intercepts, wrong y-intercept. Everything else is just kind of reversed. Number 16, they have x squared times x minus 3 quantity cubed. Everything that's wrong with this has to do with multiplicities. They have the right intercepts in 0 and 3, and they have the right end behavior for this positive quintic function. X squared times x cubed is x to the 5th. Let me actually write out this function this time, unlike how I didn't last time. So their problem is the way that your graph goes through the x-axis. The x-intercepts and end behavior are fine. By the way, with the x-intercepts being fine, an x-intercept of 0 also means a y-intercept of 0, which means that one's also fine. Are fine, but the way the graph touches hits the x-axis, hits the x-intercepts, is incorrect due to the multiplicities of each of them. So at x equals 0, keep in mind for your x-intercepts here, your x-intercept here is 0. That is a multiplicity of 2. That means it should bounce off of the 0. The 3, and I wrote this wrong, this is supposed to be cubed, not squared. That x equals 3, x-intercept has a multiplicity of 3. So this is times 2 times 3. We've now seen a lot of things regarding cubics. We've seen some snake things through multiplicities as well. Y-intercept again is 0. So this graph is going to have a different kind of appearance than that. It'll have the same end behavior. But when it hits 0 and 3, it's going to hit them differently. So at 0, it'll bounce off. And at 3, it's going to snake through it. It will start down, but it's going to bounce off that 0. So it's going to come up and down through like that. When it hits 3, it's going to do this. Not linearly through, but in cubic-like fashion, it's going to snake through more so like that. And that should be the appearance of this graph instead of what you had, not what you had, but what the book had previously. Are all the other values perfect and exact? I don't know, maybe not, but that's going to be the nature of that graph. Let's confirm this with the graphing calculator. On the graphing calculator, I'm going to type x squared times x minus 3 cubed. And so looking at this graph here, you're going to see the bounce off at 0 and the snake through at 3. You can see that it doesn't go straight through. It kind of has that curve through like that. And that's what we're getting on this one. Okay. Numbers 17 to 22, find all real zeros of the function. It says see example 2. I believe example 2 was where we used the graphing calculator and the location principle. Whereas some of these graphs here, and I kind of want to talk about the ones that are factorable and do kind of this other version as well, and then I'll go to location principle. You know, I feel like doing both. It says find all real zeros, and it doesn't give us a need to do one way or the other. So this one looks factorable by grouping. I am, for the sake of any ones that are factorable by grouping, going to use that. When I have to use rational root theorem and I don't know which number to plug in, then I can use the location principle as well. So I'm kind of an in-between. I said I would abide by the book, but the book does adhere to the entirety of the chapter as well as anything else that's involved. So here, when I factor out x squared and -1, I get a common factor of x minus 4. So x squared minus 1 is what the result of that is, and that's a difference of 2 squares, which is x minus 1 times x plus 1. So you can see that factored form is very important for what we can do here because this reveals your x-intercepts. Your x-intercepts are 1, -1, and 4. It would also reveal multiplicities, none of which exist. Your initial standard form actually reveals some good things as well. It reveals your y-intercept is 4, although you could plug in 0 into there. It reveals you have a cubic and positive leading coefficient. So you know it's going to start down, finish up. So all that stuff is involved. We have all the information that we need, and so we can sketch that graph. I'd argue this stuff is just as important as location principle. I'd argue this is actually even more important because not every class is always going to rely on graphing calculator. You do have to know these practices, and not every graph is going to be presented in standard form. So without use of table, I can get pretty much everything that I need here. I have 1, -1, and 4 as my x-intercepts. I have 4 as my y-intercept, and I have start down, finish up behavior. So it probably tops out at that guy here. If they're asking for things like local maxes and mins and stuff, I am still going to use the graphing calculator for that. I don't know if this is the problems where they do that. Oh, it just says find all real zeros of the function. All right, well, the zeros are x equals 1, -1, and 4. Okay, you know what? I might take back what I'm doing here. It doesn't even ask us to graph. So although I did all this, and this is good fun stuff, okay? Actually, let me move ahead for a second and see if it asks us to graph. These ones ask us to graph here, okay? These ones don't look factorable by grouping. So let me just state this off the bat of this last problem we just did. I might have done it a little bit differently to find the zeros in the location principle. And I will use the location principle and go back to this really quickly. But it says find all real zeros of the function, great. The zeros are the x-intercepts, right? What I did was I factored this. Factoring this gets you the x-intercepts. You probably well know that, but that is how you can do the same kinds of graphs we did in the previous set. So I did want to bring that up. Okay, so I overran 17 in the wrong way. Apologies if you said, you're wasting my time. I sure hope I'm not. That's the kind of graph you're going to have to do. Let's go back to this problem and figure out how to get the zeros of 1, -1, and 4. You know what? I'm going to leave that problem as is. I'm going to leave, like I stated, if I can factor by grouping, I'm going to do it that way. And why do I say that? The only problems you can factor by grouping look like they're the first two problems. Everything else you cannot. So I will do the other ones using the location principle there, right? They say find the zeros. Find the zeros as you need to. Number 18. And I won't graph these other ones, by the way. F of x equals x cubed minus 3x squared minus 4x plus 12. You enter my domain, you go by my rules, or you get the heck out of here. X squared times x minus 3 minus 4 times x minus 3 is the factorization, or the factor by grouping portion. And then you get down to x squared minus 4 times x minus 3. This difference of 2 squares is x minus 2 times x plus 2. Okay, therefore the zeros of this are x equals 2, -2, and 3. And that's the answer. Okay, now I will officially use location principle, where previously we would use all of concept of rational root theorem to get these values. This time we'll use the graphing calculator, and we will use the location principle to find one of the possible rational roots to use. Now, I already know one of them by looking at what the numbers are here, so I don't know how much this book is intending on us using what we're going to do here. I want to start still with the ideas of our p's over q's, guys. This is still rational root theorem at play. Your possible rational zeros of this cubic are factors of 4 over factors of 2. That means you have plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 1/2. 1 divided by 2 is that. 2 divided by 2 is 1. 4 divided by 2 is 2. So those are already there. So these are the 8 possibilities. Now, instead of plugging and chugging each individual one as you go, although it looks like one works, you could go to the graphing calculator, and you type in that function, 2x cubed plus 7x squared minus 5x minus 4, and use your table. Now my table, I'm going to do what they do. I'm going to start from 0 and go upward. The problem is at 1, you're going to see a 0 here. Now the location principle is still working in play though. You can see it goes from negative to positive, and in between somewhere it did have to hit a 0. All the ones do. So it looks like that is one of your zeros on this thing. Maybe it's the only one that is rational or real. Who knows? So that means, so h of 1 equals 0. That's by the location principle. Yes, I could have plugged in 1 into here and found out 2 plus 7 minus 5 minus 4 is 0. We're going to use synthetic division on this. This is no different than I would have done on the problem anyway, right? I would have used rational root theorem. I just went to the graphing calculator to see the result of that. And we got 2, 7, negative 5, negative 4. We'll turn this into a quadratic. Yeah. All right, so this thing is h of x equals, now it factors to x minus 1 times 2x squared plus 9x plus 4. That is factorable to x minus 1 times 2x plus 1 times x plus 4. That's 8x plus 1x is 9x, like that. So your zeros are x equals 1. If 2x plus 1 equals 0, you subtract 1 divided by 2. X equals negative 1/2, and x equals negative 4. So location principle was kind of used, kind of not used. It all depends on what we're talking about with respect to, like, we found the 0 on the graphing calculator in one of the same ways I would have done from previous problems. Let's find one that's kind of a fraction, out of reach, something like that. I want to use it the same way the examples did. Number 20. Let's see if we get that chance, basically. Okay, first of all, I see a common factor, and I'd love to pull that thing out. I can take out a 2, and I'm left with x cubed minus x squared minus 12x minus 9. That being said, we are still, whoopsie, this is a 2x cubed. That being said, we are still using the location principle. Now, we're talking about zeros only. We want to know when this thing equals 0, right? That's the only thing we care about there. So when does this equal 0? I don't care what the 2 is. 2 times 0 is still 0. So I can go to the graphing calculator and type that one in. Let's turn it on. Let's do 2x cubed. I mean, here's the thing. Because we're using the calculator for it anyway, I guess it doesn't matter. But because I'm going to use synthetic division on this thing afterward, getting that factorization helps me personally. So might as well have it smaller as long as I factored correctly, and including that 2 was very important. All right. Oh, before I go to the table, let's do this. Let's write out those p's over q's here, the rational root theorem. And by the way, keep in mind, I should use the smaller one for it. Factors of 9 over factors of 2, which means we have plus or minus 1, plus or minus 3, plus or minus 9, plus or minus 1/2, plus or minus 3/2, and plus or minus 9/2. So these are the possible ones. Now, if 1, 3, or 9, because I'm not going to look at the negatives for the sake of making this thing kind of cool if it works out the way I want it to. So let's take a look at the table now. If 1, 3, and 9 are not zeros, and I kind of hope they're not, Ah, 3's a 0, darn it. I was going to say if they're not, then I wanted to look into one of the fraction ones and talk about location principle there. But I can't go away from what they're giving me. And what they gave me is that 3 is a 0. Here, 3's a 3, Mr. Robinson. What are you talking about? It's like I'm teaching and I'm doing all this stuff, and out of context, the principal walks in the classroom. And I'm like, hey, guys, so you do agree that 3 is a 0? Everyone says, yeah. Principal goes, Mr. Robinson, can I talk to you for a minute? All right, so h of 3 equals 0. Let's use synthetic division on the 3 with 2, -1, -12, and -9. So again, what we're doing right now, unfortunately, is no different than what we've done in the past, because when they reveal a 0 on us, we are then using it. That's the unfortunate part of the biz. Maybe next time they could give us problems that don't do this. I'm sure they are going to in a moment, but just getting us started. I think they're just getting a location principle thing in mind. And I'm going to go back to that thing again, to the graphing calculator, to show you something else with that after. So x minus 3 and then 2x squared plus 5x plus 3. This 2 is factorable. This factors to 2x plus times x plus, this factors to 3 and 1. 2 plus 3 is 5. So your zeros of number 20 are x equals 3. Subtract 3 divided by 2. X equals -3 halves. That's the one I kind of wanted to seek out. And x equals -1. And the other problem is, if I use the graph portion of the graphing calculator, that too will reveal even the -1 before it reveals the -3 halves. So I was kind of at a loss anyway, no matter what. I was going to hit those. Anyway, what I'm showing the graphing calculator is, once again, the location principle is still applying. It goes from negative to positive, and in between, it has to hit a 0. Now, that doesn't mean that every 0 is always between a negative and a positive. We've seen some bounce back graphs as well. I'm just stating, if we go from negative to positive in a polynomial, somewhere in between it had to hit 0. So it makes sense that 0 is among your values, and it just so happens to be at 3. All right, let's go to number 21. Number 21, we do not have a common factor, so we will treat it as naturally as it is provided. There are a lot of possibilities when it comes to p's over q's here. Listen, I'm not going to write the p's over q's if I do land on an integer within my set. So let's go ahead and type this. We'll have to type it in anyway. So let's type this in the graphing calculator. Let's see if we get any zeros from an immediate snapshot of this. If not, I really would like to seek a fraction one to really work out the location principle as intended. Okay, let's go to the table. Let's see if this snapshot, we hit a 0 again. I can't refrain from using a 0 if they give me one, guys. That's what the graphing calculator is stating, so we're going to use it. So, and I keep stating that over and over. Why do I keep stating that? Here, take a look. Let's go back to the lecture portion of this. When we did the lecture portion of this, they did the, not here. They did the location principle thing here, and they said, look, we're going to use the graphing calculator on this, and we're going to look at the table. The table is from x is 0 to 6, and look how there aren't any zeros on y. There weren't any zeros. So by location principle, we got to discover that a 0 exists between here and here. That's what I'm trying to do on these problems right now. They're not even giving me the luxury of it. That's why on those first two questions, I said, you know what, guys? I'm just going to then factor by grouping. If they're going to not let location principle be what it serves to be, and they're still not, then let's do that. Anyway, what was my 0 for this thing? 3. So once again, 3 is my 0. I changed my equation, right? All right, this is the new equation. Okay. So g of 3 equals 0. That's among my rational values. So using synthetic division, we'll get another polynomial alongside x minus 3 to be 4x squared plus 13x minus 12. So g of x equals that. I don't yet know if this is factorable. I have no idea. I have to play with it. Let's try it. 4x times x. Now I know it's not going to be 2x times 2x, otherwise this would have been an even number. Let's try a plus and minus here. Let's try some numbers. I can't do both 6 and 2. Let's try 4 and 3. 3 would have to be here if so. That'd be 16. Oh, I said plus and minus. Why did both these turn into pluses? Negative 16 plus 3 is negative 13, so I just have to switch these signs. And le voilà. It was a le factorable, as you would say. So we do have our zeros here based on this function, and I keep writing g of x here. At some point, I'm really supposed to be setting these equal to 0. I apologize, I have not been doing that. The idea is to solve for x when that is equal to 0. So that is the true written aspect of that. Because I was thinking more of x-intercepts. We came off graphs. Anyway, add 3 divided by 4, you get 3/4. That's the one I wanted to look for. And then negative 4. Now, if I did look a little more intently at that thing, let's go and take a look back at this one, because at least this will pop up here. Let's go back and take a look at our table. If x is 3/4 and this has multiplicity of 1, that means between 0 and 1, your y should go from negative to positive or from positive to negative. I think probably actually from positive to negative because it's a positive cubic. So this one here, let's go back to the table and look at 0, which is positive, and 1, which is negative. That means that between, this is probably where I could have used it, between 0 and 1, that there is a 0 that it exists on y, so we'd have to find that x value. That's where rational root theorem would have applied. Maybe they're making us, maybe they want us to do that, and I'm just spoiling the fun by having a 0 pop up. Well, they are by the problems that they create. Let's see if we can actually have that pop up on number 22. Or let's see if we can force it on number 22. Even if 1 pops up, I'm going to use that location principle as they really want to. And I assume that's what they want us to use. It doesn't say use location principle. It says find all zeros. I guess do whatever you want to do. But example 2 did use the location principle. I don't even use that phrase location. This is the first time I've ever even said those two words together in that same string. There are other things in calculus that involves that has to do with all continuous functions that we use. That's not location principle. Anyway, let's go take a look at this one. Oh, 0 popped up. Oh, you can't see this. Sorry, I'm typing some stuff in. So I typed in my equation. I typed in my equation right here. And a 0 popped up right here at 5. Okay, let's say we didn't know that that 0 popped up, okay? Let's seek other possible rational. Well, here's the thing. I can't guarantee the other things are rational. Because a cubic can have one rational function, and then the other two can be complex. So even if, or irrational, I should say, they can even be irrational, even though between 0 and negative 1 it goes from negative to positive, that means there is a 0 exists in between, there's no guarantee that it's a rational 0. So by extent, so with that in mind, I don't know if I can use location. You know, I don't want to waste my time in trying something that might not work. So let's just use this again. I feel bad we don't get to practice the location principle. If they wanted us to use it, they should have given us problems with irrational solutions in parts and non-zeros on integers. Or whatever. They should have given us non-zeros on integers. I would have said that. At least the first sets of integers. Anyway, I apologize that I'm blasting you in the book and stuff. You're like, let's learn. Well, we're doing the same stuff we've done before. F of 5 equals 0. So in using synthetic division here, see, we started doing this 3 sections ago. We're not even graphing these. I think I graphed the first one, right? So if I'm overly personable in my videos, this part of it's because this is my first time seeing these problems. So I expected to do one thing and it's not really happening. I'm kind of like, eh. All right, this factors, oh, let's set it equal to 0 now. I got to stop doing that. It factors into x minus 5 times 2x squared plus 7x plus 3, which is also factorable. Set it equal to 0. So this is 2x plus 1 times x plus 3, because now this becomes 6x plus 1x, which is 7x. And these zeros are going to be x equals 5, x equals negative 1/2, and x equals negative 3. Okay, let's keep going. In 23 to 30, we'll graph the function, identify the x-intercepts and the points where the local maxes and mins occur, determine the intervals for which the function is increasing and decreasing. Now, we will graph using the graphing calculator because everything else is going to be based off the graphing calculator. I'm not even going to use like rational root theorem and things like that. The numbers might not even be necessarily rational to hit everything like this. So just keep that in mind when we're doing these. We are going to go straight into it here. I'm going to plot 2x, or write in 2x cubed plus 8x squared. Now I know the y-intercept is -3. -3. All right, let's see if we can see all the turning points here. If not, you have to zoom out more. All right, so we're going to have to zoom out, and by zoom out, I mean zoom up. Let's get the y values a little taller. I can, for the most part, probably even get these x values smaller. I probably don't need things wider than like 6, so we can see more of the curve on it. All right, so there's a lot more of the curve on it. We're seeing every aspect of this cubic. I'm going to go ahead and get some parts of this graph sketched out as well. Just kind of take note of what it looks like for the time being. Okay, you see it? All right, awesome. Okay, I'm gonna go ahead and sketch the graph of this thing. Now, what I do need to do, you know what? I'll sketch the graph last. I'll sketch the graph last. What I'm gonna do is write in the information so I can plot those points kind of exactly as they are. The critical points I wanna find are this 0, this 0, this 0, this local max, this local min. Then we can talk up the rest of it. They say graph the function, but my graph will be based off those, because I can get exact turns and things like that. Okay, so what do we need to find? We need to find the x-intercepts. Now, they don't look like they are on integer values. So, and I can't guarantee the rational root theorem is going to give me the numbers I want, because they might be irrational. So here's what we're going to do. We're going to use the 0 feature. The 0 feature is right here. We have to find all 3 of these. I need to pick something. Here's -1. It's just a little right of -4. So my left bound can be -4. My right bound can be -3. And I got to guess something right in between. And this is one of the zeros here. So I'm going to write these things out. So the zeros, I'm going to write x is about -3.90. So I'm doing that right here. X is about -3.90. That's one of them. I still have 2 more to get. This takes some time to do, and we have several problems to do this with. So this won't be necessarily a fast process. Now we got to do it again. Find the next 0. Somewhere between -1 and 0. So left bound -1, right bound 0. And that'll be at -0.67. So I'm just going to write these ones. You can't see it, but -0.67. And then the last one is going to be finding the 0. Maybe it's positive 0.67. Who knows? Between 0 and 1. Between 0 and 1. Positive 0.57. No relation. All right, so here are the 3 zeros. -3.90, really close to -4 like that. -0.67, about -2/3. -0.57, probably closer to a half like that. Those are the 3 zeros to plot. Now we're going to find this relative maximum, this local maximum here. So what we're going to do is go to calc. We're going to find a maximum somewhere between, -5 and 0. Who cares? We know it's the maximum value between -5 and 0. It's this peak point. So they found this one. The x value, it actually looks like it's exactly -2 and 2/3, the way that they're writing that thing out. I guess I'm just going to use the rounded -2.67. But we have a local max at -2.67 for x and 15 point, well, if you round to 2 decimal places, it's 16.00. It's not exact, but that's around it. So it's around -2 and 2/3. And then rounded to the nearest hundredth, it is 16.00. Now this thing needs to change its scale here. We'll go by 2s to get that one. Obviously, we have to do the same thing on the other side. So our local max, -2 and 2/3-ish, and around 16, that's where it tops out. So I'm not guessing where it tops out. That is where it tops out. By the way, the y-intercept of this is -3. That's another point that I could actually plot. And that's probably around the local min. So the local min is going to be this bottom point right here. So we have to go second, calc again. Minimum, option 3, somewhere between -1 and 1. Guess that smallest point right there. Okay. I think it's saying, so this negative 2.2, whatever this is saying, what this is saying is negative 0.000002. It actually does mean x equals 0. The reason for that weird bit right there actually has to do with the graphing calculator itself not being able to compute through pixelation of this graph the exact point 0. I believe that this min is not just rounded to be 0, negative 3. I believe it is exactly 0, negative 3. Just like this local max, it might actually be negative 2 2/3, comma 16. I'd actually have to use calculus to figure out whether that's true or not. But the local min of this thing here, whether rounded or not, is at 0, negative 3. 0, negative 3. So the y-intercept is that local min. We can now complete the sketch of the graph. So it's looking like that. And down through there, and it's going to bounce off of that. Again, it's not, that's, you know, it's a U-shaped bounce. I didn't probably get it perfect like that, but it goes up through there like that. There's the graph. Get a little bit taller. Didn't know if I wanted to run into the 20 or not. And I did. All right, so we have the local maxes and mins. We have the x-intercepts. We have to determine the intervals for which the function is increasing or decreasing. It's increasing all the way up until x is this value. It increases after x is this value. So its areas of increase, it increases when x is less than negative 2.67. Again, that's rounded. And that's a random alarm that freaked me out. Hold on. Okay, that's a sound I've never heard before. My clock alarm in my room went off. I think it had to do with a power outage we once had. And that freaks me out. Anyway, I don't know how that got picked up on the microphone. Sorry if, like, RIP headphone users. Why was I writing an A? X is, probably and. X is less than negative 2.67 and x is greater than 0. Those are intervals of increase. Decrease, on the other hand, is when this thing is between negative 2.67 and 0. That's why it goes from a local max to a local min. So the decrease location, x, whoops, let's write it as a compound inequality, negative 2.67 and 0 for x there. And I think that's everything we need. That is a lot for one problem. I'm just saying I think that's everything we need. Let's move forward. Number 24. Now, number 24 is one where outside of the maxes and mins, I can actually probably get this graph for you a little bit. The idea of it. Negative x to the fourth plus 3x. This one has a common factor of negative x. And you're left with x cubed minus 3. At least one part of this, I know that it's going to hit 0 as a thing. The end behavior, it's a quartic, end behavior is going to start down, finish down. I don't know how. I'm just stating that that's something that I'm noticing about the graph there. Also, this part here is going to reveal some stuff as well when it comes to another x. The cube root of 3, I guess, will be one of your things. So let me go to the calculator first and figure that out. Let's see if I've actually accomplished that. The others would be imaginary, but the cube root of 3, I don't know how to do a cube root on here. The cube root of 3, I'm expecting 1.44 to be one of my x-intercepts and 0 to be an x-intercept. So let's type in the original function, negative x to the fourth minus or plus 3x. Let's take a look at the graph. Okay, so the graph does more on the bottom than it does up top, so let's kind of change this nature here. Let's even get it a little more within. Oh, what did I do? Okay. So there's the graph. Okay. Now, it does a slight kind of slalom through there. It does hit 0, 0. I mean, we should know that based on what we're seeing here. The x-intercept of this guy is 0, period, right? That's what we have there. So I'll make sure to plot that. That's one of your x-intercepts. We got to still find out what that other 0 is, though. So we do know, as far as zeros, is that what they say? They say identify the x-intercepts. I wrote zeros before. But the x-intercepts are going to be 0, and I'm guessing cube root of 3, which was what? 1.44 or something like that? Let's find this other one. This 0 is somewhere between left bound and right bound. Yeah, looks like it's supposed to be that. And let's guess, and that's that number, 1.4422. I'll put 1.44, whatever. Although I kind of felt like I wanted to put cube root of 3. All right, those are the x-intercepts. So we have this one and about this one right here. Okay, local maxes and mins are things I wouldn't have known. Now, this graph does not have a local min. This graph goes down forever, right? That's its end behavior. It only has a local max, and it's this guy up here. So that's what we have to find on this one. Maximum. Somewhere between 0 and, I don't know, 2. And it's going to be this guy. So that's at 0.91 for x. So local max at, and I know you can't see this yet, 0.91 and 2.04 for y. Okay. So it's like that. As far as local min, guys, there is none. There is none local min. So this is 0.91 really close to 1 and 2.04 really close to 2. Probably something like that. Now remember, our graph is stretched differently, right? This graph, I changed the window range completely here. If we did it more like what my thing probably looks like. Actually, you know what? We used to do this. Negative 9.4 and 9.4. Negative 6.2 and 6.2. This was a way to actually square off your, because your calculator window is a rectangle, but this squares off your axes. Did I type something wrong again? I feel bad when, oh, scale by 1. That's why those increments go going all screwy. There we go. All right, so anyway, that's what our graph is kind of supposed to look like there as well. So this is what we're going to have there. Remember, that is a maximum. That is actually where it tops out. Meanwhile, it hits through all these values here. So it's going to be going like that a little bit, then going back down. We saw a little bit more of a strange different kind of curve thing to it, but that is at least the idea. It increases all the way up to that x value, and it decreases after that x value. I'm going to really try and improve my time on this stuff afterward. I'm getting a little sloppy. That honestly, that calculator thing, the alarm clock thing really screwed me up. It did. It's screwing up I got freaked. Now my blood is pumping higher and stuff like that. I just feel different right now. So sorry if I'm a little jittered. I'm never jittered when recording. That thing just came out of the blue. I live a silent, happy life. The only thing I ever hear is myself. And I don't know how loud it was on the on the computer, on the microphone. But it was loud here, I tell you what. All right, once again, if I'm to do something for myself right here, I do see a common factor of x. That leaves me with the knowledge that this is this has an x-intercept of 0. Has an x-intercept of 0. Now, what else it has is up to the calculator for us to determine, but I do know already when it comes to a graph that we're going to have that. So that's one less thing to worry about. Obviously, the graph is going to show it. But then that's no guesswork either. We can't say, oh, is that maybe 0.2? No, it's definitely 0. X is 0, Y is 0. Also, it's a positive quartic. That means it'll start and finish up. Something else that we'll know as a for sure. So let's go to the graphing calculator. Let's plot these things in. We're going to get x to the fourth minus 3x squared plus x. Let's see the graph for what it is. There's the 0 it crosses through, and it bounces off of that in a very distinct way. Now, it's actually I take it back. It's not bouncing off of 0. What we know, and this is an important aspect of this, what we know based off what I did through factoring is this has a multiplicity of 1. If this is a multiplicity of 1, that means it's going through 0, not bouncing off. Despite what this graph looks like, we're going to have to zoom in, guys. Despite what this thing looks like here, when I zoom in, you are going to see a curve up through 0, and somewhere it is hitting something. There it is. It's hitting 0 right here, but it's curving up and it's hitting something else. So it's just as important that we did note that there was 0, so we made no assumptions on what came next. So what else does it hit besides 0? And by the way, oh, I did mention that as an x-intercept last time. So when we list our x-intercepts out, 0 will be one of them. And everything here is rounded. You have to remember that. So my next one I'm going to find is this one right here, somewhere between -1 and -2. So let's find the 0 between -2, -1. And it's -1.88. I'm just writing them on my thing. They're all approximated, just understand that. And then we got to find that little guy right there, somewhere between 0 and 1. But I don't want to include 0. Let's see. I'll put left bound as 0.01. I want to make sure I don't hit 0. And 1. You can also guess. Whenever they say guess, I'll show you what that means in a second, just so you understand. 0.35. Okay, so here's the guess thing. If I go to calculator and do 0, what if I chose it to be between -1 and 1, right? Between -1 and 1. Those are my left and right bounds. It's going to find a 0 between here and here. When it says guess, it says get as close to your 0 as you want to be. If I'm on this right here, that means it's going to find this 0. This is the closest 0 to this point between -1 and 1. However, if I got closer to this 0, like this one over here, then it would actually get me 0 as my answer. If I enter here, it's going to give me 0, 0. That's why they say guess, because it says we might have multiple things within this range. Get as close to it as you like to do. Anyway, that's what that means. So let's find the last 0 on this thing, which looks somewhere between 1 and 2. And when I say guess here, it's just because we know it's right in between there. And it's 1.53. So we have all 4 of them plotted out, or written out. Let's go ahead and plot them. Now, we already have the one at the origin. 0.35 is pretty much right next to it. There's not much I can do on the graph with that, but we did find it. 1.53 is right there. And -1.88, pretty close to -2, is right there. Now, we do need to talk about maxes and mins. We didn't quite get to that yet. So, keep in mind, once again, because this thing topped out, it didn't top out at x equals 0. It topped out somewhere in between. Let's find that local max first. The local maximum, somewhere between 0 and 1. It's at 0.17 when rounded. So local max is at x equals 0.17-ish and y equals 0.08-ish. You know, once again, this is stuff that generally, I know we're doing it with the calculator and stuff. This stuff we generally talk about when we hit calculus. So I'm not saying it's interesting we're doing it now. It's just this is a bunch of work for these problems. It's going to take some time to do these now. So I wrote this local max like this, 0.17 and 0.08. It's all just going to be all within there, guys. You're not going to see really anything on this graph by this because how zoomed in it is. Maybe I could change its scale, but we'll leave it. Because I need to see how far down this min goes. We have 2 local mins. We have one right here. So let's find that one first. Let's find the min between 0 and 2. It's going to be this guy here. 1.13, comma -1.07. So local min, there are 2 of them. So there's 1.13, comma -1.07. But there's another one that's out of my window range. So I got to zoom out. Let's just hit zoom out. Let's zoom out here. And there's the other local min. It's also the absolute min of this graph. But when I zoom out there, I can now find that minimum. Somewhere between, I don't know, -5 and 0. It's the lowest point on this graph as a whole. So it's still going to find that one. -1.30 and -3.51. Okay. So we have all the information. Now we got to plot them out. So I got my local max, I guess, sort of. 1.13 and -1.07 is probably around there. And -1.30, -3.51 is probably about there. This graph starts up, finishes up as a positive quartic would. And then I got to do my best version of the sketch where it hits that bottom, comes up through 0, hits that top, comes down through that other 0, bottoms out again right there, and goes back up through there. Whoops. Shouldn't have such an eccentric turn, but there it is. Okay, now increases and decreases. Increases are here and here, those intervals. So this thing increases when x is between this guy and this guy. That guy is actually, remember, not 0, but 0.17. So it's between x equals -1.30 and 0.17. And then it is and then the other increase, and It's increasing when x is greater than that local min x value, which is 1.13. It's decreasing when x is less than negative 1.30. And it's also decreasing right here between x being 0.17 and 1.13. Okay. All right. Number 26. F of x equals x to the fifth minus 4x cubed plus x squared plus 2. I don't see anything of factoring note. So let's go straight to it. So x to the fifth. Okay. So the graph, kind of crazy looking. Let's change our window stuff now based off this. I want to fit the points better. Let's go from, say, negative 3 to 3 on x, and let's go up to maybe 10 on y. Or maybe 12. I need to fit some more. Let's go negative 3 to 3. I want to make this look curvier. I don't really care about what it does after the turns. So I need to see that turn and that turn there. Now I want to note that this thing doesn't look like it's peaking out or doing anything else. If I do zoom in on it for a moment, if I do zoom in on this, we're going to probably see that it's plateauing. Maybe not. If it goes up at all, if it has a bottom and stuff, I'll change it. No, it looks like it's just plateauing. So that's neither a local max nor min. Okay, I want to make sure that you're well aware of that. So I'm going to zoom back out again. Let's get what we had before. Ooh, close to what we had before. At least I think I can see everything on here, okay? Let's start with the zeros. And remember, we'll graph afterward, or we'll graph alongside it. So the zeros, this first zero is between negative 3 and negative 2. And I'm just going to write them off screen. So this first one is going to be negative 2.16, again approximated. The next zero, that actually might be a 1. So between 0 and I'm gonna say 1.5. I don't want to hit that other one there. I want to make sure I'm in between. This might be 1. It is 1. So that's exactly 1. And the next one is a little bit more, somewhere between 1.5 and 2, right? So 1.5 and 2. And that's this guy. 1.75 rounded. All right, those are my 3 x-intercepts. So I'll go ahead and plot those up. All right. So negative 2. Oh, by the way, 2 is our y-intercept. 2 is our y-intercept. So negative 2.16, 1, and 1.75. Now remember, our graph has a different scale than what the one on the calculator does. Or the graph has a standard scale. This one is not going to look. It's not going to look quite like this. Where does it top out? Where does it bottom out? There's one local max, one local min. So let's find the local max. And it's only a local max, somewhere between negative 3 and, say, 0. We'll find it. So this guy right here. Okay, it hits up there. We just can't see the cursor. I think we're just not, I think our window range just misses the appearance of it. Let's bring this back up to 12 and do the same thing. Sorry, let's let it redraw and do the exact same thing. I think it showed it. We just want to see it and be sure that it didn't clip out or something like that. So between negative 5 and 0. What did I just do? What just happened? Maximum between negative 5 and... What's happening? Why does it keep saying invalid? Hold on a second. Give me a maximum. Left bound. Oh, because negative 5 is not in our window range. I see. So that was the other problem, right? I don't want to hit the wrong value. Okay. Anyway, so I don't know if this was the same number or not, but it has a local max at negative 1.63, comma 10.47, which I guess fits in our window range, right? 10 is the top of our graph stuff, so there's that. The local min between 0 and 3. How about that? How about 0 and 2? And this bottom guy, 1.46 and negative 1.68. All right, 1.46. Negative 1.68. There's a lot to do for these problems, man. Local max, negative 1.63, comma 10.47. It's around 10.5 after the like right there. Okay, and then 1.46, comma negative 1.68. What was this number? 1.75? 1.46, comma negative 1.68. Probably about like that. All right, and it's a quintic function, and we did see the snake in between the y-intercept portion as well. There's a little bit more nature to this graph. Remember, it does top out here. It doesn't go higher. And it does a little bit of this as well. It's going to hit down here. It's going to kind of snake itself through there and into this portion right there. I'm trying to get as much as I can because our graph wasn't quite as tall looking, but that's about the appearance of the graph. Okay, we need intervals of increase and decrease. It increases all the way up here and here. It increases when x is less than, this is the max, right? Negative 1.63. And when x is greater than that min of 1.46. Come on, Tommy, beat that guy. Beat him, you got him, let's go. You got him. I shouldn't incite violence on a math channel. Now, it decreases everywhere in between. There's a little bit of a potential, I won't say hiccup, it's not wrong, but if this thing plateaus and has a slope of 0 somewhere, they can still argue that it is on the interval of decrease. So my statement will still be that it is decreasing on the entire interval where x is between negative 1.63 and 1.46. So there's a decrease the entire way through on that, even if there is a momentary bit in time, maybe on the y-intercept, where it has a actual slope of 0. All right, number 27. We're only halfway through these. Now we're hitting some ones with decimals and such, so we'll see where these go. I might need to take some sort of break here in between. I need just like rest. I need to fix my back and stuff. 0.5x cubed minus 2x plus 2.5. Give me 1 second. I want to make sure on the problem, I was thinking about saying factoring. Make sure I never factored out any numbers and used. Okay, that was a previous set. Okay, anyway. Negative 0.5 or 0.5x cubed minus 2x plus 2.5. Let's go ahead and graph that. X cubed. Now 2.5 is the y-intercept. Something to remember. I'm going to bring this back to my squared graph stuff. From here on out, I might just work on zooming in certain spots. We'll see. Okay. Oh, nice looking graph. So it is a cubic function. That's the number of turning points that we're going to have. It has one x-intercept, just one, and that's the one that we want to seek out. So that's 0, somewhere between negative 3 and negative 2. Which is negative 2.46 about. So the 1x intercept, negative 2.46. Now it does have a y-intercept, of course, of 2.5. They don't ask us to identify it, but I do want to plot it. I do want it to be a part of my graph. So 2.5 is here. Negative 2.46 is pretty much negative 2.5 on x right there. So we have an x-intercept, we have that. We need now this local max and this local min. So let's go for the local max, somewhere between, I don't know, negative 3 and 0. And that guy at top is negative 1.15, comma 4.40. So local max, sorry, I'm writing it out. Negative 1.15, comma 4. I said 40, 4.04. 4.04, and then local min somewhere between 0 and 2. 1.15, comma 0.96. I think there's something to that with respect to just the idea that 4.04 plus 0.96 is 5. I think something about shifting this up 2.5 changed the effect of what these things are. Otherwise, I think they would have been the same. And it would have been perfect. Actually, it would have. It would have been an odd function. Anyway, so negative 1.15, comma 4.04. Yeah, this is just shifted up, to whatever units. And 2.5 units. And 1.15, comma, it was 0.96, right? Yeah, 0.96, so like that. And yeah, so there is some form of symmetry. That means there's another point that would kind of resemble the reflection of this x-intercept right there, but I won't really be able to put it. So I'm going to hit this local max. I'm going to go through this y-intercept and bounce off that local min and come up out the other side of champ like that. There's our graph. It increases up to the point that x equals negative 1.5. It increases there, and it increases after x equals 1.5. So when x is less than negative 1.15 and when x is greater than positive 1.15. It decreases in between the negative 1.15 and 1.15 on x. There you have it. Okay, number 28. I'll take a water break here. All right. Number 28. F of x equals 0.7 x to the fourth minus 3x cubed plus 5x. My note, I'm not going to write it in factored form. My note is that x is a common factor. That means 0 will be an x-intercept. So I'll write that x is 0. I just won't write the factorization. But 0 is one of them. That way we know if there's anything else that's kind of crossing through and stuff. We're just well aware. So I got that set up and started. Let's keep going. Let's take a look now at the graph itself. 0.7 x to the fourth. And it's a quartic. It's a positive quartic function. Keep that in mind as well. Minus 3x cubed to the third plus 5x. All right. It's going to start up, finish up, boom, like that. It does hit some minimum that we don't see. So let's go ahead and shrink that thing down to size. Go down to negative 10, see if we can see it now. All right, so we see it all. So we have 1, 2, 3, 4 zeros to hit for this quintic function. We know that this one is 0. So let's find this one. Looks like it's a little less than negative 1. Let's say it's between negative 2 and negative 0.5. I don't want to hit 0 and get the answer as 0, so I want to get that one. So negative 1.15. It's not the same negative 1.15 as the previous problem because it has a different rounding to it. So just kind of keep that in mind. The other ones, let's see. Somewhere between 1 and 2 is another one. Let me write it down. 1.64. And the last one looks like, I don't know, just later. Let's say it's between 2. Whoopsie. What am I looking for? Calc. 0 between, yeah, between this number and, well, between this number and 8. All right. 3.79. Whenever I say something there, I'm rounding to the nearest hundredth. I hope you've recognized that. Okay. Otherwise, I've been saying that for years. Okay, let's see. We got x-intercepts here, here. See, good news, bad news with these problems is I really can't go any faster than I'm going right now. That means you're seeing both top speed and you probably get to keep up with me at the same time. Sometimes I'm going slower than I would normally need to for myself, or I'm going too fast for your own good. And I think this is kind of just right in between. Now I'm going to write out local max, local min. And based off the graph, there are 2 local mins and there's 1 local max. So when we look at this, 2 local mins and 1 local max. Let's find that local max somewhere between 0 and 2. And that's this guy right here at 0.87, comma 2.78. 0.87, comma 2.78. Okay. The local min. Now, the maximum value, I need to remind you, the y value itself is the maximum. This is where it's occurring as an entire point, though. Two local mins. One between -1 and 0, it looks like. Hopefully that's the actual bottom there. Okay, -0.68, comma -2.31. And then the other one is somewhere between 0 and 5. So this guy. 3.02, comma, ooh, this is in the way. Is that -9.3? -9.30? So 3.02, comma -9.30. Okay. All right, let's get these points plotted. Got a local max at 0.87, comma 2.78. Probably about yeah. Local min, -0.68, comma -2.31. And then 3.02, so 3, comma -9.30. Okay, about like that. So it's got a lot of ups and downs, and the y-intercept is the x-intercept, which is 0 right there. So we bottom out here. We top out here. We bottom out. We go through this point, and we bottom out here. Then we top out there as well. I'd like to get a little more curve to this one, though. I'd like to get a little more down like that. There we go. And go up and through like that. Okay. Now it's got moments of increase right here, and moments of decrease right here and here. So the increases are when x is between this local min and this local max x value. So that is -0.68 and 0.87. And then afterward, it's when x is greater than this other local min at 3.02. When x is greater than 3.02, it also increases. It decreases up until -0.68. So when x is less than -0.68. And then it decreases in between the 0.87 and the 3.02 x values. There we go. Okay, two more. Not for the set. We still have another like 30 problems to go. Number 29. H of x equals x to the fifth plus 2x squared minus 17x minus 4. No common factors, no factoring by grouping. Only thing I can see for sure is a y-intercept of -4, for which I will happily get a plotting of so I don't forget that it's there. Let's start with that. Y-intercept of -4. Let's even get some of the details ready. X-intercepts will be here. Local max here. Local min here. Increase. Decrease. Okay, x to the fifth can have as many as 4 turns. That means we might have 2 local maxes, 2 local mins, something like that. That's as many as we can have. I don't know if that's going to happen. Let's go ahead and take a look. This thing on the graphing calculator will be x to the fifth plus 2x squared minus 17x minus 4. All right, let's see what fits in this graphs window. Oh, that's quite tall. Okay, we're going to have to change this window range. We might even have to change our own scale of when we do this graph stuff as a class. Total. Let's see what happens from -30 up to 30. Let's see if we hit our maxes and mins here. This might get too tall for us. There's our top, there's our bottom, and there's the stuff in between. These are some of the zeros. -4 is the y-intercept right there. Okay, I got 3 zeros to talk about. I got a 0 to talk about right here, somewhere between -3 and -1. It might be -2. It looks like it's a little right of -2, like -1.9 something. Oh, no, other left of -2. -2.10. So I got -2.10. I have another one just left of 0 there. So between -1 and 0. I have one at negative 0.23. And then I have a final one. It might be at 2. This might be at 2. Between 1 and 3. And it's at 2. It says 1.97. So, well, it says 1.97. I don't know. Maybe it's 2. Maybe the way that it's zoomed doesn't really show it. Maybe it is 2. Maybe it's not. Do I have a way of seeing for sure? Hold on. I want to zoom in. I want to see. No. Let's zoom back out again. Sorry about this. Shoot. Let me adjust this window range, guys. I did not do what I wanted to do here. Hold on a second. Okay, I was fixing the graph to zoom the window range. This is between 1 and 3 and -1 and 1. It does not look like it's actually hitting at 2. There's 2, and it's just to the left. So I'm going to agree with what they had before. Now, I forgot what my good values were here. I think I did something like this. And if not, we'll be able to tell. Okay, so good enough for this graph. So those are my zeros that I have. Now let's find the local max, local min. So local max, let's go between -2 and -1. We get -1.46, comma 18.45. So that's pretty tall. We're going to have to change our scales of our y's, which means I'll have to change my y-intercept. It says it's at -4 right now. I'll have to change that as far as my scaling goes. My local min, same thing. What was I going to mention? I was going to say something out loud. I forget what it was. Oh, well. 1.25, comma, -19.07. Okay. All right, let's start doing some stuff on this graph. First of all, I'm going to go by, I think I saw Tom Cruise. I think it's Mission Impossible 3 now playing. Yeah, Philip Seymour Hoffman. Let's go. All right, so, here's what I was going to mention. Remember I said this was a quintic function. It may turn as many as 4 times. It only turned twice. It only turned twice. So as many as 4 times is not a guarantee of anything there. Okay, so there's my scaling of y's. I'm going by 2s. That means my y-intercept of -4 instead is right here. My x-axis is still going to be like this. So my x-intercepts of -2.1 and -0.23 and 1.97, which pretty much looks like 2 to me, are right there. My local max is about -1.5 and 18.45. Now, 18 is this number. 19 is in between those, so it's probably about like that right there. And then 1.25, 1.25, -19.07. Remember, -19 is between -18 and -20 right there. So I think that's what I have information-wise for those. Again, apologize for any violence in the background that you may see. I hope it's just purely entertainment purposes. I like to kind of peek back there every so often. Mission Impossible 3 is a great movie. Mission Impossible 2 is not. Every Mission Impossible from 3 onward are must-watches, man. That looks a little too vertical for my taste. Everyone else says from 4 onward. No. 3 is where everything starts, man. It starts with Jules. And you need to see Philip Seymour Hoffman in action in that movie, man. It's great. Look at him right now. He's just, oh, here we go. Okay, so there's the graph. Increases. Ooh, I don't know if we should show a gun. Okay, so increases. We're increasing all the way up until this local max at -1.46. So every x that's less than -1.46 and every x that's greater than the local min's value of 1.25. And then we are decreasing in between those, between -1.46 and 1.25. Like that. Okay. All right, last one, number 30 from this set. We have g of x equals, and we have a lot of terms. X to the 4th minus 5x cubed plus 2x squared plus x minus 3. Okay, let's graph it. Here we go. X to the 4th. Oh, you can't see this. Dun, 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 dun. All right, y-intercept of -3, keep that in mind, but we also have to keep our scaling in mind. So let's see what this graph reveals. A lot of that, I think that's another plateau. Let's zoom in possibly to see if that is indeed a plateau. A plateau means it doesn't increase nor decrease there. It just kind of flattens out, which means it doesn't have any turning points. It starts its decrease, and then it goes back to decreasing after. Oh, it looks like it does a little top and bottomness. Okay, so that's a change, guys. That is a local max and min in pure action. So let's do some different window changes. Let's see what just -9.4, 9.4, -6.2, 6.2 does. Now that we're very aware that there's a change, that's why we zoom in and take a look at this stuff. So discovering with you. All right, that shows it a little bit more, and there's a bottoming out. I don't know if we noticed this because our window range wasn't there. So, okay, we got to zoom out on the bottom. Let's go down to like -25 and see if we can hit that bottom. Nope, still can't. Okay, what are we going to do here? Let's go from -3 to about 6, and then let's keep going down to the bottom. -3 to 6 on X. See, this is part of the tweaks, man. There's no perfection in this ever. Let's go down to -40 and see if we hit it. Again, there's never any perfection in this. Trying to find out. There we go. Okay, now remember, there is a min here and a max here that we're going to find. There's a 0 there and a 0 there. So we're trying to seek everything about this that we can, and there are 3 turning points. They are minimalized, but they are there. I'll even let the graph show you that they're there. So x-intercept that I have right here, somewhere between -1 and 0. So we'll start with that one, between -1 and 0. And that's at -0.77. Now we have another x-intercept. Oh, the y-intercept, by the way, is -3, but I got to determine scale since this goes so low. The y-intercept, the other x-intercept is between 4 and 5. 4.54. I'm writing this stuff, so far I've written this. I guess if you want to follow along with me, I'll get this stuff pre-drawn to start with. Now, I do believe I'm going to be changing my y-axis scale. I'm probably going to go by 4s to get that bottom. So this will probably be -40 and -20 and 20 and 40. That way, the y-intercept of -3 is probably about, 3/4 of the way down right there. Now my x-intercepts of -0.77 and 4.54 are right there. A couple more things to point out. Let's keep going on this. Let's write these out. Let's write out local max, local min. Now there's one local max. There are 2 local mins. So get ready for those. At least according to what I saw from the graph before. So what I saw here, let's start with this bottommost local min. I know it's kind of hard to see from this number that's down there right now. But there's a local min down there. So let's start with that minimum, because the other max min stuff are probably hard to see. It's somewhere between, 2 and 5. I don't know where specifically, but that's why it's going to tell it for us. So it's this guy down here. So that guy down there, they're pointing at it. 3.44, -39.40. So 3.44, -39.40. That's why I have to go down to -40 for scale. Now, the other local min is, this graph does a little bottoming out and going up. We saw that on the graph itself. So somewhere between -1 and 1, it hits some other bottom that's not that local min. Actually, I don't want to go all the way to 1. You know why? I want to make sure that it goes, let's go to like 0.1. Or 0.5. This one's a little trickier when you're not fully zoomed in. But this one right here, it's going to hit some bottom here. Listen, it's always going to hit a bottom. We need to make sure that this is the lowest of the low that it has. So we just got to make sure that we're hitting that point. I believe this is -1.56. And then -3.09. So there are the local mins that I'm plotting right there. So let's get those ones. -1. Hold on. -0.16, not 1.56. -0.16, 0.16. And then -3.09. So it's really close to 0. And then -3. Yeah, it's going to go down here. Oh, that's right. These are scaled by 4s. So negative 3.09. So it's basically hitting that y-intercept. You can't see much of it right there, unfortunately. There's not much to see. The other local min is 3.44, comma, and then negative 39.40. So probably looking all the way down right there like that. And then the local max is not too far off from the x-axis either. It's kind of in this positive realm. It's the highest point between that bound and then let's just say 2. And it's going to hit some topped out point right around here, right there. 0.47, comma, negative 2.56. 0.4. Oh, you can't see what I'm doing. I'm sorry. You couldn't see anything I was talking about. But right there, it's at 0.47. I hate when I do that. Comma, negative 2.56, like that, okay? So, that one, 0.47, negative 2.56, I can probably get a little bit more maxi right there, like that. Okay, that's all I can get from the graph regarding the points. So we're going to go here, bottom out at the minimum, hit the y-intercept, top out right there, not much, but there's a little bit of it, going down here, bottoming out there, and coming back up and topping out on this guy right here. Probably more like that. And I want to fix the bottoming out portion on the left side on the decrease. And that looks terrible. All right, I want to probably do a little more like that as well. Just by what I expect to kind of see on these. I'll fix that. Okay. So there's this graph. Increases and decreases. It increases. Intervals of increase are right here. There is an interval of increase between this min and this max. Between negative 0.16 and 0.47. That's more than half an x width of increase. There is some. Does increase there. And it increases when x is greater than 3.44. Now it decreases when we are less than that first min, first before the bottoming out, x is less than negative 0.16, and then it decreases again after that maximum all the way to that minimum right there. So that is between the x of 0.47 and 3.44. Okay. Whew. Glad to be done with those problems, man. Those were interesting. Okay. All right. Numbers 31 to 36. Estimate the coordinates of each turning point. State whether each corresponds to a local min or max. Then estimate the real zeros and find the least possible degree of the function. So probably best that I copy and paste these things over. My estimations are going to be my own doing. I'm going to say as close to what I feel they are. I'm going to round to the nearest tenth, I'm sure, in a lot of these. Okay, so estimate the coordinates of each turning point. Oh, should have I stated, okay, on all these with the maxes, I should have stated this is the max, this is the min, things like that. They are the y values very specifically, but those were the turning points themselves. So, okay. Anyway. Okay. So turning points are here and here for number 9. So this one's going to be a local max. This is going to be a local min, right? So my local max, I estimate to be, this is negative 1. I estimate about negative, I don't know, 0.3, comma 0.5. That's just my own guess. Local min, probably the opposite. It looks just like an odd function, so there's symmetry about the origin. So local min, I'm looking at about probably 0.3. I don't know, maybe 0.25. Maybe somewhere, I was between my 0.2 and 0.3, and I said 0.3. How about negative 0.25? So 0.25, comma 0.5. How about that? I stated local maximum, real zeros, and find the least possible degree of the function. So my zeros, I'm estimating about negative 0.5 and 0.5. Okay. Now, because it turns 2 times, it needs to at least be a cubic. Least degree has to be 3. It needs to at least be a cubic because of the 2 turns that it has. And given that it's an odd function, It starts down, finishes up. It can't be 4. It could be 5, right? But it can't be 4, for example. All right, was that it? Estimate the coordinates of each turning point. Local max or min. Estimate real zeros and least possible. Yes, okay. All right, let's go to number 32. Okay, on number 32, excuse me. On number 32, we have turning points here and here. I don't know these turning points. These are going by 2s, though, okay? So -2, -4. Somewhere's around -3. Let me actually get rid of those for a second. I'll say around -3. So I'm seeing a local max around -3 on x. And, you know, these go by 2s as well. How about -1.5 on y? And then a local min, again, as they go by 2s. So maybe 1/2, and then down at, let's see, 2, 4, 6. Maybe this is 7, so maybe 6.5. So 1/2, and then -6.5. That's kind of as best as I can do. Zeros, there's just 1 0, and it's right there. These are going by 2s again. So 2, 4. If this is 3, maybe that's 2.5. So 0 is at x equals 2.5. Why not? There are 2 turning points once again. So that in an odd function leads us to state that this could be a cubic. So least degree is 3. Least degree is 3. Okay, number 33. A little bit different. We've been dealing with a lot of cubics lately. Well, actually, no, we've been dealing with a lot of things lately on our graphs. But when they give us a graph or a function, a lot of cubics. This one's not. Okay. What I'm seeing as the turning points for local maxes also appear to be my zeros of my function. So local max, I see 2 of them. I see one, what looks to be 1, 0, and 3, 0. Those are my estimations. That's probably what they are. 1, 0, and 3, 0. Local min looks to be pretty straightforward as well at 2, -2. Those are nice ones. Now the zeros that I have are the same as the local maxes, where x equals 1 and x equals 3. And it has 1, 2, 3 turning points, and it's an even degree function. It looks like least degree is 4, a quartic. There's number 33, the easiest of the bunch so far. They should have started with it. Come on. Number 34. Ooh. Number 34. Ooh, 34 is an interesting thing. Do you notice what it is? Look at the scale on y. That's tricky. The scale goes by 10s. Every increment is a 10. Okay, so be cautious of that when we name some things here. Let's start with local maxes. Let's highlight where they are. 1, 2. So this one is at, these go by 1s on x. So maybe -1.2, comma, maybe 5. Not 0.5, but 5. Remember, these are going by 10s here. And this one, let's say it's at x equals 2. X equals 2, sure. It may be a little less, but whatever. It's they said estimate. Y is around, I don't know, 7, 8. 8? 2, 8. Those are my local maxes. Local mins, we have 1, 2 of them here. Now this one, the x value, it's a little more than 0 this time. Let's say at least 0.1. So 0.1 comma, these go by 10s. 10, 20, 30, 40, there's 50. So maybe like -48 or something like that, going pretty low. Now it has another local min here at 1 point, how about 1.8? And I don't know, -4. Probably not -5. It's not halfway there. -4. Maybe negative. Oh, not negative. Yeah. Negative. Where's -5? Right there. Maybe -3.5. I'm going to try. I'm going to do my thing. How about -3? -3. Looking good. Too weird on estimations, man. I'm focusing too much on them. Zeros. 1, 2, 3, 4, 5 of them. 5 zeros with 1, 2, 3, 4 turns. Interesting, actually. We'll talk about that in a second. Let me, okay. Zeros. Okay, negative 2.4. Negative 1.4. Negative 1.4. I just looked at 2 was just staring me in the face. X equals negative 1. How about 1.45? I don't know. And x equals 2.5. And x equals 3. Those are my estimations there. Now, what was stated previously, I forget the name of it, but what was stated previously was you can have least degree based, it can be one more than the most number of turns you have. So we have 1, 2, 3, 4 turns, so we can have up to degree 5. It's an odd function. And this hits the x-axis 5 times as well. That means that can also be degree 5 as well. So least degree is 5, a quintic function. Sorry for the strobe effect. That's a machine gun action at you. Let's see if I can fast forward through that. It's a little flashy for us. All right, so least degree of 5 on that one. Number 35. Went from maybe the fastest question to the slowest question there. So number 35. Okay. All right, we have local max is nowhere. This is not a local maximum. It never kind of slowed itself up. It's also not a local min or anything. We have 2 local mins. No, we have 1 local min. So local max, none. Local min, right here. Okay. That is at, whoopsie. That is at, I keep fast forwarding a little bit. I don't want to see a corpse. All right, these are going by 1s and these are going by 2s. So this is negative 1.2 comma negative 2, 4, 6, 8, 10. That's 12. So negative 10.5. So negative 1 point, I'll say negative 1.25, negative 10.5. Like that. Zeros looks to be, I don't think it's at negative 2. I think it's a little more than that. I think that 0 is negative 2.05. Yeah. I think negative 2 probably hit around there. So it's a little bit more than that, negative 2.05. And definitely less than 2 here. How about 1.85? Whoops, I need to say x equals. All right. Now, based on behavior, although there is only 1 turn, a full turning point, and although it hits these 2 points here, that doesn't mean this is a quadratic. This initiated a next turn. This doesn't have symmetry here, so it's not a degree 2 polynomial. The least degree this one can be still is 4. The least degree is 4. Just because you see only 1 turning point doesn't mean it must be 2 in any sort of way. Once we're starting to see other behavior like that, it can't actually be 2. It's actually going to be 4 at the very least in that problem. Number 36, I'm just going to say, is the same way when it comes to the nature of not being a parabola, a quadratic equation. It's not exact symmetry, despite the fact there only, once again, appears to be 1 true turning point. And I want to make sure you keep that in mind. So I'm just stating off the bat, I believe this one's also degree 4 at least. So on number 36, we have no local maxes, once again. Local max, there are none. Local min is this bottoming out guy about right there. These are going by 1s. These are going by 2s. So negative 1.15. I don't know. I'm just being inventive. Negative 1.15 comma negative 2, 4, 6, 8, So negative 7's there. Negative 7.6. Okay. Zeros. We have one right here and one right here. They look to be about the same zero, a little bit less than negative 2.5 and positive 2.5. I don't know. How far over do you think? Negative 2.45? X equals plus or minus 2.45. I want to kind of be clever like that and say that. Least degree, though, is not 2. It is 4. Maybe 6, maybe whatever, but it can't be 2. You can't get a 2 out of that despite the things that you know about a 2. Okay, numbers 37 and 38. We're going to sketch a graph of a polynomial f having the given characteristics. We did some of this stuff back in section 3.1, but we didn't hear about local mins and maxes at the time, and now they're giving those things to us. So let's use the actual graph paper stuff we had before, and let's address them. I'm going to let what's written there stay written there, and I'm going to start just plotting some things on here. They said sketch a graph. It's not the graph. You just got to do what you got to do on them. Is this all the information on 37? I want to be sure that it's not on this side. Perfect. Okay, number 37. The graph of f has x-intercepts at negative 4, 0, and 2. It has a local minimum when x equals 1. So somewhere on here it has a local, local maximum. Somewhere on here where x equals 1, let's say right there, it maxes out. And then somewhere at negative 2, negative 1, negative 2, it has a minimum. Okay, let's say its minimum is a little lower, just because that's the kind of thing that happens. And they said, sketch a graph. They don't say anything about the degrees or anything, so we could absolutely just make this go through these as we wish. We have a lot of open-endedness in what you can do, guys. I want to make sure you know that. And I'm going to show you some version of that open-endedness right now. So I'm going to go through these guys, okay? Local min here, local max here. No one says this has to go through down like this. What if this does this? What if it hits right there and bounces off? We don't know. We don't know. All right, that could be your graph for 37. As long as it has those x-intercepts. Oh, you know what should show that? You know what? I take that back. It said this was its local minimum. It didn't state another local minimum. So I take it back. We're going to go through there. I said we don't know. We do know. Sort of. It says it has a local minimum. Doesn't mean it has the only local minimum. But let's honor it like it's the only local minimum that exists. Just like the x-intercepts, right? We're not adding more x-intercepts than that, so I'll leave it. Number 38. So maybe there is kind of one answer, but it doesn't matter where the max or min goes as long as it's on that x value. So number 38, the graph of f has x-intercepts at x equals negative 3, 1, and 5. It has a local maximum when x equals 1. So this is the topping. Okay, so that's telling you it's going to bounce off of that. That is a local maximum. Make sure you're aware of that. I'm going to remember it. Local minimum when x is negative 2 and when x is 4. So let's say it there, and a local min when x is 4. Maybe there's some symmetry to this graph. They look like they have equal spacing. So let's do kind of a quartic function looking thing. So it's going to have one turning point here, and then it's going to go up, and it's going to go bouncing off of this right here. And if I did this kind of right, I can probably just reflect my own graph right here. So I can take this, copy, paste, flip it over. Let's see if I can just make it as nice looking as possible. Look at that! There's a little bit of symmetry, right? Looking okay. So those are the intercepts. It does bounce off its own local max. So I was trying to be clever with the first problem at its detriment. This time, this thing requires us to be clever with the problem at hand. And there's the bounce off feature. All right, numbers 39 to 46 are different ilk of problems completely. Determine whether the function is even, odd, or neither. Now on these problems here, we're going to do it more in an algebraic realm, not a graphing realm, although I could sometimes draw them to show you what's going on here. H of x equals 4x to the 7th power. What we're going to do is substitute negative x into here, and we need to determine, do we get the same function out, do we get the exact opposite function out, or what? Because this is negative 4x to the 7th, that means that h of negative x is going to be the exact opposite of h of x. H of x was 4x plus 7. h of negative x is negative 4x plus 7. So because it's the exact opposite, that is the determination of an odd function, where opposite x's give us opposite y's. Number 40. I'll tell you the answer before it happens. Number 40 is even. I was going to say even. Number 40. G of x equals negative 2x to the 6th plus x squared. Once again, substituting negative x into here. And remember to do order of operations, meaning you do the exponent before multiplication. Negative x to the positive 6 is positive x to the 6th power. Multiplied by negative 2 is negative 2 times x to the 6th. So that stayed the same as it did before. Negative x quantity squared is positive x squared. When you add that, it's still plus x squared. What you had before is what you still have now. That means g of negative x is the same thing as g of x. What's that telling you? This function is even. It has symmetry about the y-axis because opposite x values give you the same y value out. You can reflect it across the y-axis and you'll get the exact same function. Number 41. F of x equals x to the 4th plus 3x squared minus 2. F of negative x would equal negative x to the 4th power plus 3 times negative x squared minus 2. Because they're all raised into even powers, they keep their signs whatever they were. So positive x to the 4th plus 3x squared. That minus 2 stays minus 2, but guess what? Same function as it was before. So f of negative x equals the same thing as f of x. Therefore, like number 40, this too is an even function. Number 42, you have f of x equals x to the 5th plus 3x cubed minus x. Substituting negative x into these ones, notice how these are all odd exponents. It's not that they all have to be odd, but notice that when they are odd exponents, you'll have change in sign. A negative number raised to an odd power will change its sign to negative. We're going to change this to negative as well. Adding a negative is subtraction. And we are going to subtract this negative, which becomes addition. If I factor that negative out of here, you're going to be left with x to the 5th plus 3x cubed minus x. The important aspect of that is that that was the original function, x to the 5th plus 3x cubed minus x. That means our f of negative x is the opposite of f of x. So we're getting the opposite y's for the opposite x's. That's what an odd function does. This is an odd function. Number 43. Number 43, we have g of x equals x squared plus 5x plus 1. When I substitute negative x into here, I get negative x squared plus 5 times negative x plus 1. And, whoopsie, the opposite of negative x squared is x squared. The opposite of, 5 times negative x is negative 5x, and then plus 1. You'll notice these stayed the same, and these stayed the same, but these did not. If only one part changes, then that means it can't be even. If you factor out a negative and you don't get the same result as what you had there when you factor it out, it's not going to be odd either. G of negative x doesn't equal g of x. G of negative x doesn't equal negative g of x. This is a neither case. It's neither even nor odd. That doesn't mean anything bad. And in fact, I don't know how much you heard it on the lecture portion. This is an even degree function. It's just not an even function. It doesn't have symmetry across the y-axis. That's all that it means. Number 44. F of x equals negative x cubed plus 2x minus 9. When I substitute negative x into here, we get the opposite of negative x, which is cubed, plus 2 times negative x minus 9. Opposite of negative x cubed is negative x cubed, but negative x quantity cubed is negative x cubed. The opposite of that is positive x cubed. Plus 2 times negative x is minus 2x, and minus 9 here. This sign changed, but this sign did not. Because not all three signs changed, factoring out the negative will not completely change things, and it's not completely identical, so this is once again in neither case. Okay, before I move on to the final two problems in this section, I want to do some pattern recognition with you. Now, I note that what I'm going to talk about might take more time than it would if I didn't talk about them before. Let's do some discovery together. What did even cases look like? What did odd cases look like? What did neither cases look like from the original problems? Here was number 39. Let's start with odds. Number 39, what did the original problem have? 4, I don't think we have to worry so much about the 4, right? That's not going to change signs, but x to the 7th, right? 7th power. How about the other odd? It had powers 5, 3, and 1. Okay? Now look at the even functions. It has powers 6 and 2. And then it has also powers 4, 2, and 0, right? X to the 0. Now look at the neither cases. You have powers 2, 1, and 0, and 3, 1, and 0. This is for polynomials only. For polynomials, what pattern are you observing to determine even versus odd functions? Let me write it, and we'll use it. In polynomials, and only treat this for polynomials. This might not be true for anything else, because polynomials are the ones that are raised to whole number exponents. In polynomials, if every term is of even degree, then it is, if every term has an even number exponent, that includes 0, including 0. 0 is an even number, and it's a constant. Then it is an even function. If every term has an odd number exponent, not including 0, but including 1, then it is an odd function. So, not every even degree polynomial is an even function. Not every odd degree polynomial is an odd function. But every even degree polynomial, every even function that's a polynomial will only have even number exponents. Will be of even degree only. Will be an even degree polynomial, etc. So when you look at these, when I go to numbers 45 and 46, number 45 is a polynomial of just even numbered exponents. You know what number 45's function is going to be? Even. I'm not even going to plug them in. This is going to be even. Are you allowed to do that? I don't know. That's why I did the problems beforehand. There's another reason I did the problems beforehand. Not every problem that you do, guys, will be a polynomial. This is true for polynomials. This might not be true for rational functions. This might not be true for radical functions. This might not be true for logarithmic functions. There are a lot of different ones. Now, one is odd and one is even. We didn't really talk about that. If it has a combination of both is when, I was going to write odd. It has a combination of both. If it has a combination of both, that is when it's in neither case. That is when it's in neither case. That's what we're looking at on that one there. So for polynomials, you can use that. I don't know if you're allowed to. But that pattern does hold true. They might even ask that on a future question. We still have 9 questions to go. Number 47. Using tools probably generally means graphing calculator. When a swimmer does the breaststroke, the function, that's a massive function for something regarding breaststroke. I'm going to copy paste that. I might have to write some stuff later, but the function here models the speed s. Yes, it does. Models the speed s in meters per second of the swimmer during one complete stroke, where t is the number of seconds since the start of the stroke, and the time is between 0 and 1.22 seconds. So it's a very light model all told. It's not being used for a lot of time, just 1.22 seconds. But they want some aspects of the curve, I guess. Parts of when you're getting there and there, whatever. I don't know which one the breaststroke is. Use a graphing calculator to graph the function. At what time during the stroke is the swimmer traveling the fastest? So they're basically asking for a maximum during that interval, right? So we'll go to the calculator. I got to type this whole thing in, and I'm going to totally change my window range as well. Now, I do see a common factor of t, or x, if you will, which means that t equals 0. There's there's an x-intercept at 0 to the 6th minus, sorry, I'm going to type this whole thing out, which is probably also the slowest speed, because that's just when it starts, and that makes sense that that's when it would start, because you have no speed at no time, right? Not much to do on the problem, but there's a lot to type in for that one part of the problem. That's why I almost wish we lived in the problem longer, in that I wish we got to do more in the question, because that was a lot to type in, and I hope I didn't make a mistake in typing it. All right, it says graph the function, but first of all, our time's only going to go between 0 and 1.22. I don't really care about anything else beyond that. And then here, I don't know, we shouldn't have negative speed at all, right? So let's just go from 0 to 6 and see what's going on there. Maybe it's too tall, too small, I'm not sure. So here's our graph. It goes from the origin. It's doing some curvy stuff, and because it's a 7th degree polynomial, it can have as many as 6 turns. Maybe not at this stage. That was actually a pretty good window range for what we're doing. All right, so cool. Pretty cool polynomial. At some point, I guess that's when you stop speeding through the breaststroke. Oh, is the breaststroke the one where you just do it once? You just do it once and you see how far you can go? I think that's it, and that's what it's showing. It's slowing down. Maybe you can do it twice. Maybe one's a leg kick, one's an arm kick. Anyway, the maximum's up here, right? This is, I can literally just do the maximum between 0 and 1.22. I don't have to do anything else. Let's just find the maximum between, sure, left bound there, and right bound, let's just say 1.2. Somewhere between there, between that arrow and that arrow, is that maximum we're going to find. And we are hitting that maximum there. So let me see the question again. At what time during the stroke is a swimmer traveling the fastest? They didn't ask for the speed. The question is t. The time is about 0.948 seconds. Maybe 0.95 seconds if they were using it like a stopwatch or something like that. We'd probably instead say that. This is the max speed. This is time of max speed. I got to write that significantly better. My handwriting has to improve, guys. Time of max speed. At least that time you don't have to ask what it says, even though the handwriting still sucks. Okay, that's number 47. Total calculator usage. Number 48, using tools. Probably total calculator usage. Okay, 48. During a recent period of time, the number S in thousands of students enrolled in public schools in a certain country can be modeled by that, where X is the time in years. Use a graphing calculator to graph the function. Describe how the public school enrollment changes over this period of time. So probably things about turning points will be involved. There are probably as many as 2 turning points here, because you can see it's a cubic function, and there shouldn't be a comma at the very end of this thing. So let's see if I can address some of what that is, just because I'm nitpicky like that. But yeah, what we probably, because I don't know what their model is, I don't know what this graph looks like, but they're probably going to say, oh, the school enrollment was going up over this period of time, and then after this period of time started going down again, and then it started to go up at the tail end of it. Stuff to expect like that, right? By the way, school's enrollment was 36,300, actually. This is all public schools. 36,300,000 were enrolled at year 0. Is X in years? Yeah, at year 0 to begin with. Remember, this is in thousands, so don't forget that aspect. Okay, let's go ahead and do that. Let's do 1.64. At least they're actually X's. X cubed minus 102 X squared plus 1710X plus 36300. Okay. Window range from 0 to 41 are the X's. We know this goes up to 36,000 something. I don't know what it does after that. So we know we're talking about big Y values, guys. I'm going to keep at 0 here. Let's go to like 70,000 and just see what's going on with that. So totally different kind of things going on here. Yep, there are the 2 turning points, and I think that's good enough for what we have. Let's diminish the Y window range, though, to really just look at that a little bit more. I'm sure 30,000 is a good low. Let's go down to 55,000. See if that works. Get a little more curve action. Okay, That looks pretty good. So in this set, I'm going to try and describe as much as I can when it comes to the starting amount, the final amount, and the two turning points, okay? So I'm going to say this stuff out loud, and I'm going to type it meanwhile and see if you can make sense of it. Actually, let's do this. Let's copy and paste that graph. But I got to go back and forth to the graph because I have to get you to see what those other numbers are. Or I can compute them for you, if that's okay. I'll compute them for you, and then you can, trust them when I get those maxes and mins. You've seen me do a lot of maxes and mins so far, right? Right. So, okay. So what are they saying? The number S in thousands of students enrolled in public schools in a certain country. In this country, so at year zero, there are 36.3 million, right? It's number in thousands, students enrolled in public schools in a country. This increases to, and here's what I want to find out. I want to find out what it increases to, what year, and how many. So I'm going to find the maximum. I'm going to look for this guy right here. And actually what I'm going to do is I'm going to color code everything. There are this many on year 0 right there. The next thing I'm looking for is right here, this maximum. So I'm going to do this over on my calculator. You don't really need to see it necessarily. So this goes from like 0 to 20. I'm just going to tell you what the numbers are. So this increases to, and now this number for Y is about 45 million. About 45 million students by year 12. It says 11.6. So around year 12. And then slowly decreases. So let's find that minimum. So 45 million around year 12. Are those blue? Those are blue. And then slowly decreases, let's do green, to this minimum. Let me find that one. The minimum is 40. So around 40 to about 40 million students by year 30. It says 29.8. So by year 30. So that's the initial portion of this. And then I want to state what it ends at, because there is an increase after that. Year 30, 40 million students. Okay, so right here, it increases again to something million. I'll say million by at year 41. So let's see where it finishes up at there. I'm going to find the value when X is 41. 47.9 increases to about 48 million. 48 million students at year 41. Okay, so that's my description of all of that. I wanted to make sure to hit all of those points and make sense of it for y'all. I don't know if that's the best description, but there are faster increases than there are decreases, and it talks about maxes and mins, the turning points within. Okay, number 49, writing. Why is the adjective local used to describe the maxes and mins of cubic functions? Why is the adjective local, which is used to describe the maximums and minimums of cubic functions, sometimes not required for quadratic functions? Well, I want you to recognize that a quadratic function, a parabola, like this one, or like this one, it has a max or a min, right? But the max and min isn't necessarily just local, it's the absolute one as well. In quadratic functions, the local max min is also the absolute max min. I know it's not necessarily a phrase that you know yet. We talk about local and relative, things like that. I don't know if you heard that. But in cubic functions, when you have local maxes and mins, they are never the absolute maxes and mins. So you need to account for what they actually are. So in cubic functions, in cubic functions, local maxes and mins are never absolutes, the absolute max extremes of the graph, but they are the highest, lowest points in relation to the points around them. Right, so that's the difference between the two. This one here is also the absolute ones. So, you can just call it max min, you're good. This is not the max of the graph. Understand the graph goes higher than that at some point. Cubics have to. They have end behavior that always does this or this. There is never an absolute max or min of any odd degree function ever. Polynomial. Quadratics will always have some sort of absolute max or absolute min, one or the other based on what you have. And it might have some relative ones, but the quadratic specifically, its max or min relative will also be the absolute. Good question for them to ask. All right, number 50. How do you see it? The graph of a polynomial function is shown, no doubt. Maybe a cubic. Find the zeros, local max, and local min values of the function. So I'm looking at zeros at -3 and 0. So zeros, this is part A, by the way. X equals -3, X equals 0. Local max, I mean, they're having us kind of rough it out again. Local max is about at -2 comma, these go by 5, so probably 4. Local min is at the origin. Compare the x-intercepts of the graphs to y equals f of x and y equals negative f of x. Now, in y equals negative f of x, this would take this graph and it would flip it over, right? It would take this thing and it would instead go here and up through there and bounce off like that. So this would be y equals negative f of x flipped over like that. So what do they say? Compare the max and min values. The max is now opposite, right? Is -2, -4, if that's indeed the number. And then the local min is the same. So as far as this, flip y value, change its sign. It's the opposite y value. The local min is the same because it's still at 0, 0. Part C, compare the max and min values. Oh, I'm sorry. This is part C, what I just answered. I was probably reading C when I said B. Part B, compare the x-intercepts. They have to be the same, of course. The x-intercepts are the same. Whoops. Now, why is this? Because changing a y value to its opposite when the y value is 0 doesn't do anything to it. Right? They don't ask why, but they're saying what they are. Now, when you tell by flipping it over like that, it's the same. So this is part C, where you have that information right there. Sorry about that. I just read the wrong part. Okay. Number 51, making an argument. Your friend claims that the product of two odd functions is an odd function. Is your friend correct? Explain your reasoning. Well, no. Because my friend is never correct anymore. No. My friend is not correct. When you multiply two odd numbers, you do indeed get an odd number. However, when you multiply two odd functions, you are multiplying the variables with exponents that ultimately add together. And an odd plus an odd does not equal odd. It equals an even. So x cubed times x to the fifth, right? Let's say I have an odd function with an x cubed, an odd function with an x to the fifth. I multiply them. I don't get x to the 15th. I get x to the 8th. You get an even function. Well, it doesn't mean it's an even function. This doesn't guarantee It is an even function, by the way. It is simply even degree. At least. At most, at worst, at least, whatever. At best. There you go. Okay, number 52. Modeling with mathematics. You are making a rectangular box out of a 16-inch by 20-inch piece of cardboard. The box will be formed by making the cuts shown in the diagram and folding up the sides. You want the box to have the greatest volume possible. So we've seen questions where we did the cutting and folding up stuff. So that means when we're talking about volume, so it says how long should you make the cuts? So when it comes to our volume, guys, we're doing a length times width times height thing. Now, the length times width can be our 20 and 16 parts, but we're cutting X inches deep on either side of them. So what we're doing is we're getting a length of 20 minus 2 X's times 16 minus 2 X's, those are the widths. The height of this is just going to be any of those X's folded up. So times height of X. So when I work this thing out a little bit more, I'm going to kind of play a factor game on this to start with here, if you don't mind. I'm going to factor out a 2, and have that X factored out. So I got 4X. I'm going to factor out negative 2's. So this will be X minus 10 here, and this will be X minus 8. So again, factor out a 2, a negative 2. Factor out a negative 2, factor out a negative 2, bring that X over. Okay. Easier for me to work off of even if I write it as a standard form polynomial. I don't know which one I should do or which one is better, but this would become 4x times x squared minus 18x plus 80, which then becomes 4x cubed minus 72x plus, or x squared plus 320x. So either we write it like this or like this, and we can do some stuff off of it. They said, how long should you make the cuts? We're going to find out what X value maximizes this volume, whether we write it like this or this. The graphing calculator is going to help us find that maximum. I'll just type the one that's in standard form. We got that one. So we have 4x cubed minus 72x squared plus 320x. Let's go to the graph. I don't know what to do with this specifically. I don't care about y values that are... I don't know what volume's going to be like. Let's go to 1,000 because volume can get pretty fast, pretty tall, pretty fast. It can't go more than certain inches deep. Let's go to like 8. Let's see if we can see anything from there. That actually looks pretty good. I didn't anticipate that. So this is just from 0 to 8. Actually, I should go farther because... Wait, how deep can it go? Let's go back to this for a second. How deep can X actually go? X can't go any deeper than 8 inches, right? Because that's kind of what I was saying. If it goes 8 inches here and 8 inches there, then you have no more width of this thing, right? So the most it can go is 8. So it doesn't matter that I have an x-intercept of 10, right? I have x-intercepts. I have x-intercepts of 0, 8, and 10. It doesn't matter about the 10. It doesn't matter what's beyond 10. What's going to happen is, and that's probably why the original function here matters so much that I actually treat this for what it is. 16 minus 2 times 10 is a negative value. So we really got to ignore that within our domain. Our domain has to be between 0 and 8, and it can't be 0 and 8 itself either. So I'm looking only through within here. That way this part of the graph is best. Listen, the graph does still, as a cubic function, it still goes up after that. It goes underneath 10 or whatever. But the maximum needs to be somewhere around here. That's what we're looking for. So the one between 0 and 8 somewhere. Left bound 0, right bound 8. And the max of this. 420.11. So your part A, how long should you make the cuts? You should make them about 2.94 inches. Cuts should be around 2.94 inches. Okay. Oh, you know what I should have done? Let me take all this, well, never mind. Forget what I just said. Yes, cuts should be about 2.94 inches. Okay. Part B. I was going to say I should solve this cubic because I can factor out and solve the quadratic, but then I realized those are the x-intercepts. That's not the maximum value. Part B, what is the maximum volume? That was this other number right here. Maximum volume is around 420.11 cubic inches. So max volume is around 420.11 cubic inches. What are the dimensions of the finished box, part C? If x is around 2.94, the length would be 20 minus that number. 20 minus 2 times 2.94. The width would be around 16 minus that number. And the height would be that number. Now I'm going to try and use kind of the exact value that I can. But these are all rounded here, right? Rounded, rounded, rounded. These are all in terms of inches. So my more exact number that I have here, 2.94, 49492. EIEIO, 2.94, 49492. Let's store that as x. So let's do 20 minus 2x and 16 minus 2x. I'll still round to the nearest 2 decimal places. And we'll call that 14.1 and 10.11. 14.11 inches and 10.11 inches. Sorry, I forget how long I've been on one screen versus the other, but now I'm back on this screen here. So here, height, width, and length. Those are the dimensions of the finished box. That times that times that should be around our 420 number, I suppose. I guess. Okay. All right, number 53. Quonset huts. Quonset huts are temporary, all-purpose structures shaped like half cylinders, like this. You have 1,110 square feet of material to build a Quonset hut. The surface area S of a Quonset hut is given by S equals pi r squared plus pi r L. But that's a cone. This isn't a cone. Sorry, wait, hold on. What? This is a half cylinder. This is the surface area of a cone. Are you sure that that's the surface area of a Quonset hut? Okay, fine. I thought it was going to be something else, but okay. Maybe, oh, you know what? Maybe half cylinder surface area is that, but that's okay. All right, SA equals, I write SA instead of S. Pi r squared plus pi r L. Substitute. Oh, I was like, there's no, okay, anyway. Substitute 1100 for S, and then write an expression for L in terms of R. So what we have to do here, sorry, these are times where I should read the problem before I give it to you. We got to solve for L. R is going to be in the answer. So I'm going to first subtract pi r squared from both sides. I'm going to write pi r L equals, and we'll have 1100 minus pi r squared. Then we're going to divide both sides by pi times r like that. So now we'll have L equals 1100 minus pi r squared over pi r. This is an option to write. An alternative option to write to this is you get 1100 over pi r, and then you subtract, pi's cancel out and some r's cancel out, and then you just get that. So here's an option, and here's an option. Depends on if you want a common denominator or not. They're both kind of the same thing, but that's part A. Part B. The volume V of a Quonset hut is given by volume equals 1/2 pi r squared times L. Write an equation that gives V as a function in terms of R only. So this is one where I've got to decide which one I prefer more. I guess the common denominator, and then we'll see what to do with that. V equals 1/2 pi r squared times L. We're going to substitute this in for L. So V will equal 1/2 pi r squared times 1100 minus pi r squared all over pi times r. Now, the pi here can cancel with this one. One of the r's can go away with this r down here. We just have 1/2 r multiplying into this whole thing. So if I distribute this, 1/2 r times 1100 is 550r minus, and this is 1/2 pi r cubed. So that's what I'm going to write for now. That's after distribution. Depends on if you want it factored or distributed. Part C, find the value of r that maximizes the volume of the hut. So this will now be our function. We're going to substitute it into there, and I don't know where our limit is. Our limit is 1,100 square feet. Well, 1,100 is already used in our thing. I don't know what our domain range restrictions are just yet. Let's go to the calculator and just see what it's looking like as a graph. 550x minus 1/2 pi times r cubed, or x cubed. All right. I don't know how this window range is going to do. Let's see what's going on. Whoop, that's shooting up pretty high there. Let's do some zooming out here. 0 to 50, because why not? I don't know what's going on. That's going pretty high up. Let's go 30,000 and see what kind of curve we're doing. Okay, I don't need that much there. All right, I only need from there to there. So let's see. That's probably about 0 to 20 we'll probably do. And we can definitely go lower. Let's go about 5,000. Hey, not bad. Hey, pretty good there. All right. I assume this is the part that maximizes volume there. Let's go to the maximum. From there to there, somewhere in between those. Find the value of r that maximizes the volume of the hut. The value of r is 10.8. So max volume, r equals 10.8 feet. That maximizes the volume. Now, with a problem like that, you know, what I did from the previous problem, and I probably should have gone back to it, I said max volume is this many. Oh, yeah, that was cubed. Never mind. I'm good. All right, so I'll leave it be. Okay, number 54. I think that was it. Okay, number 54, thought-provoking, which normally means open-ended. Write and graph a polynomial function that has one real zero in each of the intervals between -2 and -1. So probably -1.5. 0 and 1, and 4 and 5. Is there a maximum degree that such a polynomial function can have? Justify your answer. The second question I don't think is very related to the first part of the question, outside of the fact that we have 3 x-intercepts, but the polynomial that we write is kind of up to us. So when it comes to these here, between -2 and -1, I'm going to state an x value of -1.5 because reasons. Between 0 and 1, you know me, x value of 0.5. I'm going to go halfway in between all of these. 4 and 5. Let's do 4.5. All right. They said write and graph a polynomial function that has one real zero in each of these. Now, because all of these are divided by 2, I'd love to also get a vertical stretch of 8. I'd love to impart factors of 2 into these ones and make this one integer values. So they'll still have these zeros. So I'm going to put f of x equals 8 times x plus 1.5 times x minus 0.5. This isn't a requirement, but I don't want to deal with decimals, times x minus 4.5. Now, what I can do is 8 is 2 times 2 times 2. What if I take these 2's and distribute them into each of these quantities here? Suddenly, what was factored for me, that's fine. That still has those zeros. Suddenly, this becomes 2x plus 3 times 2x minus 1 times 2x minus 9. I'd much rather deal with these than I would with the other ones. Now I still have to graph this eventually. I got to graph either this one or the way that it's written. I'll use the graphing calculator for it. But at least here, my numbers will be clean for me to go with when it comes to me expanding this out, which is what I'm going to do next. I'll multiply 2x plus 3 times these two after multiplied together. That's 4x squared minus 18x minus 2x minus 20x plus 9. And then distributing that, that's 8x cubed minus 40x squared plus 18x plus 12x squared minus 60x plus 27. All right, so this one will have 8x cubed minus 28x squared minus 42x plus 27. So there's my result. I am going to graph that. It looks like I do need to change scales, unless I want to now divide everything by 8. Maybe I was like, you know, I just didn't want to deal with decimals when multiplying. Now I'm good with it, and now if I divide by 8, I feel all good. I'll leave it like that. We'll just go ahead and graph it like that. It was open-ended, and I even chose my x-intercepts to begin with. So let's go to the graphing calculator. Let's plug that in. 8x cubed minus 28x squared minus 42x plus 27. And let's confirm that my graph even did what it was supposed to, that it hits those x-intercepts. So probably between -2 and 6 will be good for x values. The y values, I think, have to stretch a little bit because of the 8s, because of the 8 that's there. Let's see if this is tall enough. Oh, not quite tall enough on that bottom end. It goes pretty low, but it did hit a top. So -100, is that enough? Oh, even still not enough. Wow, this goes deep. Let's go -150. So when it said graph, I'm probably not going to use like, well, I can still use my graph stuff. It's fine. All right, there we go. So is this -1.5? Totally. That's -1.5. That's 0.5. That looks like 4.5. Okay, so those look like the values there, but we probably need to find those maxes and mins. When they say graph, because of the section that we're in, they're probably really deep in saying, let's find all those other values that belong in there. So I'm starting to get my graph ready. Now let's come up with this local max, and I'll be changing the scale of my other stuff, from -2 to 0. There's definitely a local max somewhere sitting up there. It's at -0.597 and 40.392. So I'm going to write this, or I'm going to start graphing some of this. Hold on. What was my first one? Between -2 and -1. So -1.5 was here. Sorry. So here's what I'm doing. -1.5, 0.5, and 4.5. I got a max at, I'm going to go by, how low does that graph go? -150? I'm going to go by 20s. So this is 100, and this is 200. Okay. So this is 40.39. So that means these are all 20s. So 20, 40. -0.59 is probably about right there. So there's my local max. I got a local min down here somewhere. So let's find that one. That is, where's my left bound? That's fine. Right bound 5. 2.39 comma -135. So 2.39 comma -120, 140, -139 is basically about right there. All right, so it's a cubic function. It's a positive cubic function, very stretched out. See, this is what multiplying by 8 did to it. Made everything 8 times taller. If this was 8 times smaller, that maximum wouldn't have been around 40. It would have been around 5. This minimum wouldn't have been around 130. It would have been around probably 18 or something like that. I don't know. I don't really know how 140 divides by 8. But, you know, it would have been less than. Probably something that could have fit on one of my taller graphs. But there's the graph itself. Is there a maximum degree that such a polynomial function can have? Justify your answer. You know, no. There's no maximum degrees. There are minimum degree, yes. There's no maximum degree, though. How come? Because any of these, remember, these were my original factored form. I could have this to the 5th power. I could have this squared. I could have this cubed. And it raises the degrees with those multiplicities. And of course, and listen, it doesn't matter what we chose for these numbers. They just said play with this and do some things with graphs. I don't know what they wanted us to do with them. But these things themselves can have multiplicities to them. So there is no maximum degree. I chose the minimum degree, actually. There is no maximum degree because each x-intercept, because each 0 can have multiplicities up to whatever value we so desire. The minimum degree, however, is 3. Not that they asked, but I'm telling them. All right. And the last question we have is number 55. A cylinder is inscribed in a sphere of radius 8 inches. That probably means the cylinder rim, the circle, is actually touching the sphere itself. Write an equation for the volume of the cylinder as a function of h. Find the value of h that maximizes the volume of the inscribed cylinder. What is the maximum volume of the cylinder? Now, what they're showing you is a radius of 8 inches. Here's my first, because I don't know what to do specifically yet. Here's my first thought in discovery is, as they're showing you 8, they're showing you from the center of the sphere to any edge of not just the sphere, but the rim of the cylinder, right? The base edge, the circular part. That means that in a right triangle sense right there, we can kind of build a right triangle, do that kind of thing, which is important for a couple reasons. Number one, this helps us find r. Keep in mind, this is 8, but this helps us find r in some sort of way. Now, because r is a part of what we do for volume of a cylinder, right? For the volume of a cylinder. But what we also can recognize here is this center. If this is inscribed in here, this center going out to here is the same distance as going out to there. Therefore, this distance is the same as this distance. And if this whole thing is h, then this guy right here is half of h. This is h over 2, or 0.5h, or whatever you want to put. So that's what's important to me. And they said, write an equation for the volume as a function of h. So that means that I need to turn my r in terms of h. I can write Pythagorean theorem and say r squared plus h over 2 squared equals 8 squared. But I need to get r by itself in this case. R squared plus h squared over 4 equals 8 squared is 64. So r squared equals 64 minus h squared over 4. Now, we could go for a common denominator. I don't know if it'll be helpful or not. Sometimes I question that, maybe. I probably only need r squared as well. I probably don't actually need r. For volume of a cylinder is pi r squared times h. Volume is pi r squared times h. So if I just use my r squared that I have right here, then I can substitute it in there. So my volume can be pi times 64 minus h squared over 4 times h. And you could do some distribution things here if you want to. I don't know. We could leave it like that. Let's see. Let's make it a cubic. I'll even call the h squared over 4 1/4 h squared. So pi, but I'm going to leave the pi on the outside and literally on the right side. I prefer pi being over there. So let's do 64h minus 1/4 h cubed pi. That's my go-to with this. That's what I believe to be the case based on what we're seeing in this setup. The r here, by the way, is not the radius of the sphere. It's the radius of my cylinder. Keep that in mind, that being half the height. So that's what I have for this. Write an equation. Find the value of h that maximizes the volume of the inscribed cylinder. What is the max volume? So now we're going to compute this in our graphing calculator. A lot of this section's been a lot of graphing calculator stuff, and I'm cool with it. Totally cool with it. I was really hoping the initial stuff when it came to graphing, though, to be a lot of get things factored and graph at a factored form. These are just my closing thoughts of the section, because I know that that's something that's heavily emphasized in what we do, given what we had from those other graphs, or given that what I saw in other books at the very least. And maybe I'm misrepresenting this by the other books. I'm thinking more about the other books with this. All right, what's my R? I'm just going to go up to 10 and figure out what's going on. I don't care about negative volumes either. Let's see what's going on here. Let's go up to 100. See what's happening. Whoa, that shoots up way higher than 100. Way higher. That shot up immediately. Okay, let's try that again. That pi, pi changes things as well, but even more. Let's go to 10,000. That thing is not quite as tall as 10,000. And it looks like I might need more than 8 or 10 as my thing as well. Let's go to 20. Let's go back to about 1,000. 10,000. Oh, higher than 1,000 though. Man, this thing's interesting. 2,500. Sometimes investigative work has to be what it is. Okay. Given it's a negative cubic, this will be our maximum that we're looking at right there. So when we hit maximum, let's go left of that at 0, right of that at 20. And let's guess in between. That's an x value or an h value of 9.24 about. Max volume. So h should be at about 9.24 inches to maximize volume. And the maximum volume you'll have is at what? 2. It's on the calculator, but 1238.22. 1238.22 cubic feet. Now, if there's something I need to triple check on this to see if I have anything close to maybe being not the right answer, but a reasonable answer, I want to see what the volume of the sphere is as a whole, because the volume of the cylinder has to be less than the sphere. And it doesn't look like it's much less than the volume of the sphere. It depends on what you have to do to maximize it. But the volume of the sphere is 4/3, because if this is less than it, and this is a problem, 4/3 pi r cubed. You have to remember that that one has 8. So 4/3, I'm doing this on my calculator, times pi, because we already multiplied by pi, that's in our function, times 8 cubed is, hopefully it's more, it's 2144.66. So this is about half of that, but it looks like that's as best as we can do to maximize it, at least based on what I'm seeing there. So yeah, that's what we're going to be doing. And remember, that says inch. Hold on. This should be cubic inches, not cubic feet. Inches on that thing right there. So that should be the final answer. I feel good to go with that. All right, guys, and that'll do it for this one. This is Mr. Robinson. Thank you so much for watching. We have one more section to go on this, section 3.9. I believe it's modeling with polynomial functions, something along that name. And then we got a heck of a lot of review in the chapter test and cumulative assessment. So thanks. Take care. I will see you in the next one.